good evening, wherever you're listening from. I hope the day has loosened its grip a little. If you enjoy these long, quiet journeys into the stranger parts of the past, you can like the video, subscribe, or leave a comment telling me where you're listening from and what time it is there. No pressure at all. I just like knowing where these stories end up. Tonight begins with a machine that should have gone silent. In 1859, telegraph operators on some lines disconnected their batteries because strange electrical currents were interfering with their equipment. The machines kept working. Messages continued to move through the wires, and above those wires, across enormous stretches of the world, the night sky had turned red. At the time, almost nobody understood that the glowing sky and the misbehaving telegraph belonged to the same event. What had happened was far larger than a failed battery, a bad wire, or even an unusual aurora. The sun had disturbed the electrical environment of the Earth strongly enough for human technology to notice. The uncomfortable part is that in 1859 there was very little electrical technology available to notice it. Today there is almost nowhere left for that current to go unnoticed. But before we bring the storm into our own world, it helps to understand the one it first encountered. The electrical age of 1859 was still young. People knew electricity, of course. They had seen lightning all their lives. They knew what static felt like. Scientists had spent decades studying current, batteries, magnetism, and the strange relationship between them. But electricity had not yet disappeared into daily life. It was still something people could notice. A wire was a wire. A battery was a battery. The telegraph office was a place where electricity was deliberately made useful. There were no power stations feeding millions of homes, no household sockets, no refrigerators humming through the night, no mobile networks, no satellites, no global electrical grid tying entire countries together. The telegraph was one of the few technologies that stretched electrical conductors across truly long distances, and that alone made it revolutionary. Before telegraphy, information had to travel with something physical. A letter moved because a horse moved. News crossed an ocean because a ship crossed the ocean. A military order, a business instruction, a personal message, all of it had to be carried. Distance meant delay. There was no way around it. Then telegraph wires began to spread along railways and roads from city to city, across fields and through forests. For the first time, information could outrun the person carrying it. A message could arrive hours or days before a traveller. Prices could move before goods moved. Railway stations could coordinate traffic. Governments could speak across distances that had once required long journeys. The telegraph did not simply make communication faster. It changed what people expected time to feel like. That expectation changed quickly. Human beings are very good at this. A miracle appears. Everyone is astonished. A few years later, someone is angry because the miracle is running late. By the 1850s, telegraph operators were part technician, part interpreter, part repairman. The offices they worked in were not futuristic spaces. They were practical rooms, wooden desks, paper, ink, brass fittings, wires, relays, chemical batteries, operators sitting close to the equipment, listening carefully to clicks that had to be turned back into language. A good operator learned to recognize the character of a line. Signals could be weak. Interference could appear. Weather could affect performance. Connections loosened. Insulation failed. Batteries deteriorated. Grounding caused trouble. A damaged wire somewhere miles away might reveal itself only as a poor signal at the desk. So when telegraph systems began behaving strangely during the last days of August 1859, there were ordinary explanations available. That matters. Most unsettling events do not begin with the impossible. They begin with the inconvenient. A signal is unreliable. The current seems too strong. The key sparks. The operator checks the battery. Someone inspects a connection. Another person blames the weather. Only later do the ordinary explanations begin to fail. And by then, Something unusual had already been happening on the Sunday. Astronomers had been watching a large group of sunspots move across the solar surface. Sunspots were not a new discovery, but there was still something unsettling about seeing them carefully. To the naked eye, the sun appears simple. A bright disk, reliable, almost featureless. Through the proper observing equipment, that simplicity disappears. Dark regions appear, irregular shapes, clusters, structures large enough that the scale becomes difficult to understand. A small dark mark on a projected solar image can represent a region larger than the Earth. The page stays manageable. The reality does not. One of the astronomers following these spots was Richard Christopher Carrington. Carrington was doing the sort of patient work that rarely feels historic while it is happening. He observed sunspots regularly. He recorded their positions. He drew them. He was interested in their movement across the solar surface and in what those movements might reveal about the sun itself. On the 1st of September 1859, he was examining one of the largest and most active sunspot groups. He was not looking directly at the Sunday. Instead, he projected the telescopic image onto a surface where it could be studied safely. This gave him a small, controlled image of something unimaginably large. Then, shortly before noon, two brilliant patches of light appeared inside the sunspot group. They were unusually bright, bright enough to stand out against the projected image of the solar surface itself. Carrington's first reaction was cautious. He suspected something might be wrong with his equipment. That instinct is worth keeping. When a careful observer sees something unprecedented, the safest assumption is often not that nature has suddenly become extraordinary. It is that the instrument is misbehaving. A reflection, a flaw, a mistake. Carrington checked. The bright patches were associated with the solar image. They were real. And because the phenomenon was so unusual, he wanted another person to see it. He left briefly to find a witness. By the time he returned, the bright areas had already changed. The entire visible event lasted only a few minutes. Another observer, Richard Hodgson, independently saw the same kind of sudden brightening from a different location. That second observation mattered. Two astronomers had seen something extraordinary on the sun at nearly the same time. Today, we recognize what they witnessed as a rare white light solar flare. Carrington did not have that modern explanation available. He had only the observation, a sudden brilliant event on the solar surface. Then it faded, and his room remained completely ordinary. No sound reached him from the Sunday. No vibration crossed the floor. No heat wave arrived. No pressure changed in the air. He had just watched an enormous release of energy on a star roughly 93 million miles away, and physically, nothing around him seemed different. This is one of the strangest details in the entire story. A violent event happens on the Sunday. The observer can draw it. The light fades. He goes on with the day. Around the world, people continue eating, working, sleeping, travelling, arguing, trading, repairing fences, watching children, waiting for trains. Nothing in ordinary life announces that something has happened far away. And something larger was indeed moving outward from the Sunday. A solar flare is only one part of the picture. The electromagnetic radiation from the flare travels at the speed of light and reaches Earth in a little over 8 minutes. But large solar eruptions can also launch enormous clouds of magnetized plasma into space. Today we call them coronal mass ejections. That term did not exist in Carrington's world. Neither did the modern concept of the solar wind. The magnetosphere was not understood. The detailed physics connecting solar activity to geomagnetic disturbance had not yet been worked out. Carrington had seen the beginning of a chain whose later links were still invisible to 19th century science. And the eruption associated with the Great Storm appears to have travelled extraordinarily quickly. Typical coronal mass ejections may take several days to cross the distance between the Sun and Earth. The 1859 event seems to have done it in something closer to 17 or 18 hours. The exact timing cannot be known with the precision we would expect from a modern spacecraft. There was nothing positioned between the sun and Earth measuring the incoming plasma, but by any reasonable reconstruction, it was exceptionally fast. The reason may lie partly in what had happened before. The sun had already been active. There had been earlier eruptions. Geomagnetic disturbances had already occurred in late August. Auroras had already been seen. One possibility is that previous solar material had altered the environment ahead of the later eruption, allowing it to travel through space more efficiently. The great storm may have been made worse by events that came before it. That is a useful detail, because large disasters are often like this. The final event gets the name. The earlier conditions quietly prepare the way. By the evening of September 1 and into September 2, Earth was about to discover what Carrington had seen. But the first sign most people noticed was not electrical. It was visual. The sky changed. Auroras appeared across extraordinary distances, far beyond the regions where people normally expected them. Reports came from low latitudes. Places where an aurora was not part of ordinary experience suddenly found the night illuminated by something that looked more like fire than weather. This was not necessarily the gentle green curtain people now associate with northern travel. Many historical accounts emphasize red, deep red, large areas of the sky glowing, bands and rays, columns, changing forms. At lower latitudes, intense red auroral light can dominate because of the altitude and geometry of the emissions being seen, but the people standing beneath it did not need the physics to know the night looked wrong. And night in 1859 was much darker than night is for most people now. Outside towns, there were no highways glowing along the horizon, no industrial parks, no bright suburbs, no skyline of illuminated towers. When the moon was absent, darkness could be profound. That meant a sudden bright aurora had more power to alter the entire appearance of the landscape. A road became visible, a field changed colour, windows filled with strange light. People woke, and because the aurora appeared so far from the places where it was familiar, some observers had no simple explanation. The most obvious comparison was fire. If a horizon turns red at night, something may be burning. A town, a forest, a warehouse. People would naturally look for smoke, flames, bells, riders, some physical source. But the glow could occupy too much of the sky. It could move in ways firelight did not. It could form arches and rays. Stars might still be visible. The category would begin to fail. Historical reports describe people comparing the light to blood, fire, flames, dawn, and luminous clouds. These comparisons tell us something important. When people cannot explain a phenomenon, they describe what it resembles. They borrow familiar images. The sky becomes a fire because fire is understood. It becomes dawn because dawn is understood. It becomes an omen because uncertainty invites meaning. One widely repeated account describes miners in the Rocky Mountains waking during the night and believing morning had arrived because the sky was so bright. They began preparing breakfast. That story should be treated for what it is, a historical account, not a measured brightness reading. But it captures the human confusion beautifully. A person wakes. There is light. For most of history, light and time were intimately connected. You did not check a phone. You did not glance at a digital clock glowing beside the bed. The sky itself was part of the clock. Morning meant light. Light meant morning, so the body responded. Someone got up. Someone began preparing food. Then the false dawn refused to become dawn. The colour was wrong. The stars were wrong. The light came from the wrong place. The night had given correct instructions in the wrong order. There are also reports of people being able to read by the auroral light. Again, these are human descriptions, not laboratory measurements, but they tell us how startling the illumination seemed. And across the world, newspapers began collecting accounts from people trying to describe something that exceeded their everyday vocabulary. At the same time, telegraph operators were facing a much less beautiful version of the same event. Currents became unstable. Signals were difficult to send. Electrical disturbances appeared across long lines. Equipment sparked. Some operators received shocks. Paper was reportedly ignited in some telegraph offices. The wires were doing something they had never been designed to do. The broad physical reason is now familiar. A severe geomagnetic storm causes rapid changes in Earth's magnetic environment. Changing magnetic fields produce electric fields. Those fields exist across the ground. Long conductors can develop voltage differences across large distances. The telegraph system, with wires stretching for miles between grounded points, was almost perfectly shaped to notice. The operators had built a communication network. Without knowing it, they had also built a detector. The longer the line, the more opportunity there was for the disturbed electrical environment to become part of the circuit. And then came the detail that made the entire event unforgettable. On some lines, operators found that normal battery power could be disconnected and messages could still be transmitted. The Boston-Portland line became the famous example. The telegraph was working on current induced by the geomagnetic disturbance itself. This should not be described as the machine working without electricity. There was plenty of electricity. That was the problem. The machine was working without the electricity the operators had intended to supply. The source had changed. Imagine the practical confusion. The line is misbehaving. The battery seems to be making matters worse. So the operator disconnects it. The circuit should go quiet. Instead, the key still responds. Signals can still pass. The system has become easier to use after removing the power source. Even now, with all the physics available to explain it, the scene feels slightly haunted. In a 19th century room lit by lamps, surrounded by brass equipment and paper, it must have felt stranger still. The newest communication technology on Earth had suddenly acquired a power source no person in the office controlled. And outside, the sky was red. The people involved could see the effects. They could touch them. They could sometimes feel them through a shock from the equipment, but they could not yet place all the pieces together with confidence. Carrington himself was cautious about claiming a direct causal connection between the solar flare he had observed and the magnetic disturbance that followed. The timing was suggestive. The coincidence was extraordinary. But extraordinary coincidence is not automatically proof. That caution matters. Modern retellings often make the story cleaner than it was. Carrington sees the flare. He realizes a solar storm is coming. The telegraphs fail. The mystery is solved. History was not that tidy. The observations came first. The explanation took longer. That is often how science really advances. Something happens. People record it. Arguments begin. Measurements accumulate. The explanation becomes better. And only later does the event acquire the clean outline we use when telling the story. The people under the aurora were not living inside a finished explanation. They were living inside uncertainty. And yet they possessed one enormous protection that no scientist had designed. Their civilization was only lightly electrified. The telegraph system was vulnerable because it was one of the few long electrical networks available. Most daily life did not depend on electricity. Water did not generally require a vast electrically controlled municipal system to reach every household. Food was not stored in refrigerators connected to a national grid. Money did not require electronic authorization. Travel did not depend on satellite timing. Hospitals did not rely on electrically powered systems in anything resembling the modern sense. Cities did not require networks of traffic lights, elevators, pumps, servers, mobile towers, and data centers merely to continue ordinary routines. The storm found the wires. There were not many other places for it to go. This is why 1859 occupies such an unusual place in technological history. A few decades earlier, there might have been too little infrastructure for the storm to leave such a dramatic technological record. A century later, there would have been far more infrastructure to disturb. The event arrived almost perfectly at the boundary between two worlds. Enough electricity to reveal the danger, not enough electricity for the danger to become systemic. And that is where the old story quietly turns toward us. Because the sun did not become more dangerous after 1859, we simply kept building more wires, longer wires, higher voltages, electrical grids stretching across regions, radio, telephone, satellites, GPS, digital finance, automated logistics, data centers, aircraft depending on radio and navigation, farms depending on satellite guidance, hospitals depending on continuous power, cities depending on pumps, buildings depending on elevators, people depending on phones that depend on towers, that depend on electricity, that depends on a grid, that depends on enormous machines designed to operate within very specific electrical conditions. The telegraph operators of 1859 accidentally discovered that a natural disturbance could enter a long human-built electrical system. We responded over the next century and a half by building much larger ones. That does not mean we were foolish. It means electricity was useful, very useful, useful enough to become invisible. And once a system becomes invisible, its failure becomes much more surprising. If a Carrington-level storm were moving toward Earth tonight, the first difference would be knowledge. We would see it. We would detect the flare. We would observe material leaving the Sunday. We would estimate its direction. We would model its arrival. We would issue warnings. Scientists would know far more than Carrington did. Grid operators would know what the old telegraph operators could not. Satellite companies would prepare. Airlines would watch. Most people would still be living normally. The coffee machine would work. The lights would stay on. Traffic would move. Phones would charge. Outside, the sky might still be perfectly blue. And somewhere between Earth and the sun, something enormous would be approaching. This time, we would know it was coming. The harder question would be what, exactly, it would find when it arrived. If a storm like Carrington's were moving toward Earth tonight, we would know far more than the people of 1859. That sounds reassuring, and it is, but only up to a point. The modern sun is watched constantly. Space-based observatories monitor active regions. Instruments measure X-rays. Telescopes track sunspots. Coronagraphs can show enormous clouds of plasma expanding away from the solar surface. Scientists compare speed, direction, structure, and past behavior. Models estimate whether a coronal mass ejection is likely to strike Earth and when it may arrive. In other words, we are no longer waiting for the telegraph key to spark before realizing something has happened. We can watch the event begin. But the strange part is that seeing a storm coming is not the same as knowing exactly what kind of storm will arrive. A solar flare and a coronal mass ejection are related, but they are not the same thing. The flare is the sudden release of electromagnetic energy. X-rays and other radiation travel at the speed of light, so the first effects at Earth can begin in a little over 8 minutes. There is effectively no advance warning against that radiation once the flare itself is seen. The radiation and the news arrive together. For most people at ground level, this part of the event is not physically dangerous. Earth's atmosphere absorbs the radiation very effectively. But the upper atmosphere responds. The ionosphere changes, and that can interfere with radio communication. This matters particularly for systems that rely on high-frequency radio over long distances. Aircraft crossing oceans or polar regions may depend on these signals. A pilot might try a routine transmission and hear only static or a weak response. The aircraft still flies. The passengers still sit in their seats. Nothing outside the window looks wrong, yet the communication environment has changed because of an event on the Sunday. That pattern appears again and again with space weather. The first failures are often not dramatic. They are conditional. A system still exists. It simply becomes less dependable. Behind the flare, however, a much larger structure may be travelling outward. A coronal mass ejection can carry billions of tons of magnetized plasma. It expands as it moves through space. It is not a compact projectile. It is a vast, evolving structure. And if it is directed toward Earth, the journey usually takes far longer than the 8 minutes required for light. Depending on its speed, the trip can take days. A very fast event can arrive much sooner. Carrington's storm appears to have been one of those unusually fast cases. The best reconstructions suggest a journey measured in well under a day. That speed becomes easier to understand when we remember that the Great September Storm may not have been moving through ordinary conditions. The sun had already been active. Earlier eruptions may have disturbed the space ahead. The later event could have travelled through an environment that had already been altered. This idea sounds unusually specific for a storm from 1859, but a modern event gave scientists a useful comparison. On the 23rd of July, 2012, the sun launched an exceptionally powerful eruption. Earth did not take the direct hit. A spacecraft called Stereo-A did. The event was fast, intense, and important enough that researchers immediately compared it with the most extreme historical storms. Evidence suggested that previous eruptions had helped clear or modify the path ahead, allowing the later CME to retain extraordinary speed. The 2012 event is valuable because it removes one comforting illusion. Carrington was not a peculiar product of the 19th century. The sun still produces very powerful eruptions. The reason July 2012 is not remembered as a global disaster is not that the event was imaginary. It is that Earth was not in the right place to receive the worst of it. Planetary geometry can be a surprisingly important form of luck. The sun rotates. Active regions move across the visible solar disk. An eruption launched when a region faces Earth can become our problem. The same region several days later may launch something just as violent into a different direction. The energy still exists. The plasma still travels through the solar system. But Earth has moved. The event becomes data instead of disaster. If a similarly powerful eruption were Earth-directed, the first phase would be an exercise in waiting, not helpless waiting. Informed waiting. Scientists would estimate an arrival window. Grid operators would receive alerts. Satellite companies would review procedures. Airlines might begin planning for possible route changes. Certain spacecraft might be placed into safer operating modes. Critical infrastructure operators would begin watching conditions more carefully. And ordinary people might see headlines long before they see anything unusual in the sky. That is one of the awkward consequences of modern warning. Information arrives early enough to be useful. It also arrives early enough to become confused. A headline may say a powerful CME is heading toward Earth. Another may say a solar superstorm is coming. Someone online will say the grid is definitely going down. Someone else will say the warning is meaningless because nothing happened during the last storm they remember. Both conclusions may be premature because speed and size do not tell the whole story. The magnetic field carried inside the incoming solar material matters enormously. Earth has its own magnetic environment. The magnetosphere forms a broad region around the planet, compressed on the side facing the sun and stretched into a long tail on the night side. The solar wind is always interacting with it. Most of the time, that interaction remains within ordinary bounds. During a severe storm, far more energy can enter the system. One of the key factors is the orientation of the magnetic field inside the arriving CME. A strong magnetic field directed southward can interact especially effectively with Earth's field. That allows magnetic reconnection to transfer energy into the magnetosphere more efficiently. The result can be a much stronger geomagnetic storm. And here is the uncomfortable part. We can often see a large CME leaving the Sunday. We can estimate its speed. We can estimate when it may arrive. But the precise magnetic structure that will determine how strongly it couples with Earth is difficult to know far in advance. The storm can be visible for many hours, while one of its most important properties remains uncertain. Modern spacecraft positioned upstream from Earth help with this. Near a region called L1, about 1.5 million kilometers toward the Sun, instruments sample the solar wind before it reaches the planet. They measure speed, density, magnetic field. They provide a direct look at what is coming. 1.5 million kilometers sounds like an enormous warning distance. By normal human standards, it is. By solar storm standards, it may translate into something closer to tens of minutes. A fast CME can cover that remaining distance quickly. So there is a strange sequence to modern space weather forecasting. We may know for a day that something large is approaching. Then, close to the end, direct measurements tell us more clearly whether the magnetic orientation is especially dangerous. The warning narrows. The uncertainty narrows with it. And somewhere in a control room, numbers on a screen change from concerning to bad. Strong magnetic field, high speed, sustained southward orientation. At that point, the preparation that began earlier becomes much more urgent. Grid operators may change power flows. They may reduce loading on vulnerable equipment. They may bring additional voltage support online. Maintenance may be postponed. Staff may be put on alert. Satellite operators may delay maneuvers or place spacecraft into protective configurations. Airlines may avoid routes where radio, navigation, or radiation conditions could become more difficult. All of this can happen while the public still sees nothing. That is the most unusual part of the waiting period. The event may already have become serious for professionals before it has become visible for everyone else. The sky is ordinary. The threat is not. Then the CME arrives. Not as an explosion anyone can hear. Not as a wall of flame. The solar wind conditions around Earth change. The magnetic field changes. The magnetosphere responds. Currents intensify. The auroral region begins expanding away from the poles. The upper atmosphere absorbs more energy. And eventually, for millions of people, the first convincing evidence may appear overhead. The aurora, a major geomagnetic storm, can push auroral displays far beyond their usual territory. People who have never seen one may suddenly find the northern or southern sky filled with colour. The first reaction is often delight, and it should be. An aurora is beautiful. It is one of the few ways a person can look up and directly see evidence that Earth is interacting with the Sunday. In an ordinary, strong storm, the spectacle may be the main human experience. People drive away from city lights. Families wake children. Photographers fill roadsides. Social media fills with images. A geomagnetic storm that sounds ominous in a technical bulletin becomes a night of green and red light. This happened on a remarkable scale in May 2024. A series of solar eruptions produced the strongest geomagnetic storm in more than 2 decades, reaching the highest category on NOAA's operational scale. Auroras were seen across unusually large regions. People who had never expected to see them from home suddenly had them above cities, suburbs, and farmland. And yet the modern electrical world did not collapse. This matters. A G5 storm is serious. It does not mean apocalypse. The category marks a threshold. It is not the physical limit of what a geomagnetic storm can be. 2 storms can occupy the same broad category while differing substantially in duration, magnetic orientation, rate of field change, and technological effect. The 2024 event caused real disruption. Navigation accuracy degraded in some places. Satellite operations were affected. The upper atmosphere expanded. Aviation and communication systems had to be monitored. Grid operators paid close attention, but there was no global blackout. That is useful evidence because it makes the modern Carrington question more precise. The relevant question is not whether a strong storm can disturb technology. It can. The question is how much farther the disturbance has to go before systems begin losing the ability to compensate. One place where May 2024 made the invisible problem unusually visible was agriculture. Modern farming may seem like an odd place for space weather to matter. The field is on the ground. The tractor is on the ground. The seeds are on the ground. But precision agriculture increasingly depends on satellite navigation. A modern tractor can use highly accurate positioning to follow planned rows, reduce overlap, manage spacing, and repeat paths with precision that would be difficult for a human driver to maintain for hours. During the storm, some farmers experienced significant GPS-related problems. The tractor still ran. The engine was fine. The field had not changed. The satellites were still in orbit, but the positioning system became less reliable. That is a very modern form of failure. Nothing looks broken. The output simply becomes uncertain. A position that is wrong by a few meters may barely matter to someone driving to a shop. The same error can make precision planting useless. Modern infrastructure is full of these differences. The question is rarely whether a system works at all. It is whether it works within the tolerance the user needs. A navigation system can be acceptable for one task and unusable for another. A radio link can be degraded but not absent. A power system can remain online while individual transformers experience stress. A satellite can survive while its orbit changes enough to require correction. And that last effect is especially strange. During a geomagnetic storm, energy deposited in Earth's upper atmosphere causes it to heat and expand. The atmosphere does not rise around buildings in any noticeable way. The change happens far above us, where low-orbiting satellites move through extremely thin gas. Even a small increase in atmospheric density matters there. Satellites travel at enormous speed. Extra atmospheric drag slows them slightly. Their orbits can change. In February 2022, a group of newly launched Starlink satellites encountered increased drag after a geomagnetic disturbance. Most of that batch was lost. The satellites were not burned by the Sunday. They were not struck by a giant electrical pulse. The upper atmosphere became denser than expected. They lost altitude. This is one of those mechanisms that feels almost too indirect to be satisfying. The sun becomes active. Earth's magnetic environment changes. The upper atmosphere heats. The atmosphere expands upward. Machines in low orbit encounter more drag. Some fall. The chain is long. The consequence is simple, and as low Earth orbit becomes more crowded, this sort of effect matters more. Modern space is full of infrastructure, communications satellites, Earth observation satellites, weather satellites, scientific spacecraft, commercial constellations, military systems, objects whose work is invisible to most people until they fail. Geomagnetic storms can affect these systems in several ways. Radiation can interfere with electronics. Charging can produce anomalies. Sensors can become unreliable. Satellite operators may place spacecraft in safe mode. Orbital drag can increase. And after particularly strong events, the radiation environment around Earth itself can change. Measurements after the May 2024 storm revealed temporary additional radiation belts. The visible aurora faded. The near-Earth particle environment remained altered. This is a useful reminder that the storm is not over simply because the sky looks normal again. The beautiful part may end first. The technical consequences can continue. Aircraft face a different version of the same problem. At high latitudes, Earth's magnetic shielding is less effective against energetic particles. High-frequency radio communication is also particularly important on routes where ground-based alternatives are limited. A significant solar event can therefore affect polar aviation through communication, navigation, and radiation concerns. Airlines may reroute flights. For a passenger, the experience may be almost disappointingly ordinary. The flight is longer. A connection is missed. The route on the screen curves differently. Someone becomes annoyed at the airline. The cause may be solar activity. Large natural events often become small personal inconveniences before they become anything more serious. This is another reason the modern Carrington scenario should not begin with cities going dark. Before the grid becomes the central concern, the storm would already be touching a scattered collection of systems: radio, navigation, satellites, aviation, precision agriculture. These effects would not necessarily happen everywhere at the same intensity. Some people would notice nothing. Others would notice that one system they rely on had become less trustworthy. The disturbance would spread unevenly through technology, and that unevenness could create false reassurance. A person looks around. The lights are on. The phone works. The car starts. They conclude nothing serious is happening. Meanwhile, somewhere else, a satellite operator is dealing with anomalies. A farmer has stopped using precision guidance. A pilot has changed route. A grid control room has begun monitoring currents it would prefer not to see. The storm exists at several scales at once. For the public, it may still be a beautiful sky. For infrastructure operators, it may already be a test. And eventually, as the geomagnetic disturbance deepens, the oldest part of the Carrington story returns. The wires, not telegraph wires this time, high voltage transmission lines. The same broad physical principle that allowed currents to enter telegraph systems in 1859 can affect modern electrical grids. A changing magnetic field induces electric fields at the surface. Long grounded conductors respond. Geomagnetically induced currents enter networks. And modern power transformers were not designed with 19th century telegraph currents in mind. They were designed for a very different kind of electricity. This is where the scale of the problem changes. A failed radio link is inconvenient. A navigation error can be serious. A satellite anomaly is expensive. But electricity is the system beneath almost everything else. Lose it for long enough, and the secondary problems begin multiplying. That possibility is why the quiet numbers appearing in grid control rooms matter more than the red sky outside. By the time most people are admiring the aurora, operators may already be watching the first signs that the storm has entered the wires. And unlike 1859, those wires are carrying far more than messages. And unlike 1859, those wires are carrying far more than messages. They carry the energy that keeps cities visible at night. They feed pumps, hospitals, data centers, traffic systems, elevators, factories, rail networks, refrigeration, communication towers, and the quiet collection of machines we almost never think about because they work so consistently. Most of the time, the power grid is successful enough to disappear. You press a switch, a light comes on, the transaction feels immediate, almost private, as if the electricity had been waiting inside the wall for you. In reality, it may have travelled through a network stretching hundreds of kilometres, passing through substations, transformers, switching equipment, transmission corridors, and control systems that are constantly balancing generation against demand. That balancing act never really stops. Electricity is being made and used at almost the same moment. If too much is generated, the system reacts. If too little is generated, it reacts. If a large transmission line fails, power does not simply stop caring about its destination. It shifts onto other available paths. A modern grid survives ordinary failures precisely because it is not a single wire. It is a network designed around the assumption that something, somewhere, will eventually go wrong. Lightning strikes. Equipment fails. Trees fall. Ice accumulates. Wildfires threaten lines. Generators trip. Maintenance takes equipment out of service. The grid deals with these events every year. That is important because it means a geomagnetic storm does not arrive at a helpless machine. It arrives at a system built by people who already expect trouble. The difficulty is that this kind of trouble behaves differently. A broken transmission line is local. A severe geomagnetic disturbance can place stress on very large areas at once. And the reason begins beneath our feet. When Earth's magnetic field changes rapidly during a major storm, electric fields are induced near the surface. The ground conducts electricity, but not evenly. Different regions have different geological structures and different electrical properties. Some kinds of rock allow current to move more readily. Others are comparatively resistive. That means the same geomagnetic disturbance can produce different geoelectric effects in different places. The ancient geology underneath a modern transmission system can influence how much electrical stress that system experiences. It is one of the more elegant inconveniences of space weather. A transformer designed in the 21st century may have to care about rock that formed hundreds of millions of years ago. Nothing about the rock is malfunctioning. Nothing about the sun is malfunctioning. The problem appears in the relationship between them and the wires we placed across the surface. Long transmission lines are especially relevant because distance allows voltage differences to build across the system. Currents can enter through grounded points and flow through equipment not designed for this particular kind of electrical behavior. These are geomagnetically induced currents. Compared with the alternating current the power grid normally carries, they change slowly enough to behave almost like direct current. Large transformers do not appreciate this. A power transformer is built to transfer energy between voltage levels using alternating magnetic fields. Under normal conditions, the magnetic flux in its core moves back and forth in a controlled cycle. Add a quasi-direct current, and that cycle becomes distorted. The transformer can be pushed toward partial saturation during part of each cycle. Once that begins, several things can follow. The transformer can draw more reactive power. It can produce harmonics. It can heat. Protective systems may respond to abnormal conditions. Voltage can become harder to control. The details are technical, but the human consequence is simple enough. A machine that normally performs an invisible task may begin consuming the electrical stability that the grid needs to keep everything else working. And this is where popular disaster stories tend to become impatient. They jump directly to exploding transformers. That can happen under some failure conditions, but it is not the normal first step, and certainly not an automatic result of a geomagnetic storm. More often, stress develops, temperatures rise, readings change. Protection systems operate. Operators make decisions. Equipment may be disconnected before it is damaged. The dangerous part is not only the condition of one transformer, it is what happens when several important pieces of a large network begin becoming difficult at the same time. Suppose one transmission element trips. Power shifts elsewhere. Another corridor now carries more load. Reactive power reserves become thinner. Voltage drops in part of the system. Operators compensate. Another piece of equipment sees conditions it does not like. Protection acts again. Most of the time, the grid is designed to keep these events from cascading. But if the disturbance is broad enough, the network can begin running out of comfortable alternatives. This is not theoretical. In March 1989, a powerful geomagnetic storm struck Earth and produced one of the clearest modern demonstrations of what space weather can do to a large electrical system. The most famous consequence occurred in Quebec. Hydro-Quebec operated long, high-voltage transmission lines carrying power from hydroelectric generating stations in the north toward major population centres farther south. The system also sat across geology that made it particularly exposed to geoelectric effects. During the storm, geomagnetically induced currents entered the network. Protective systems began operating. Important reactive power support was lost. Voltage stability deteriorated, and the collapse happened astonishingly fast. The Quebec grid went from operating to widespread blackout in roughly a minute and a half. That is one of the most useful details in the entire modern Carrington discussion because it makes the scale human. 90 seconds is not long enough to hold a meeting. It is barely long enough to understand that the first problem is not the only problem. A control room can receive an alarm, then another, then another. Protection systems respond in fractions of the time a person needs to make sense of the screen. The network begins to separate. Then the lights disappear. Millions of people lost power. For someone sitting at home, the cause would not have looked cosmic. The room simply went dark. Heating stopped. A clock went blank. The refrigerator fell silent. Streetlights disappeared. The experience was local and domestic, even though the chain of cause began with the Sunday. That contrast is worth keeping. Nobody experiences a geomagnetic storm as an index. They experience the secondary system that fails. A pilot hears poor radio communication. A farmer loses precise positioning. A satellite operator sees orbital drag. A homeowner hears the refrigerator stop. The science operates at planetary scale. The human experience arrives through ordinary objects. The 1989 outage did not last for months. Power was restored within hours. Quebec did not become permanently uninhabitable. The event did not destroy modern civilization, but it demonstrated that a geomagnetic storm much less extreme than the strongest reconstructions of 1859 could interfere seriously with a modern electrical grid. And that left an obvious question. What would a larger storm do? The honest answer is not satisfying enough for disaster fiction. It depends. It depends on the exact storm. It depends on how quickly the magnetic field changes. It depends on how long the dangerous orientation persists. It depends on which regions are facing the strongest effect. It depends on geology. It depends on grid topology. It depends on which transmission lines are heavily loaded. It depends on what equipment is already out for maintenance. It depends on transformer design. It depends on operator action. It depends on season and demand. It depends on how much warning was available and whether the warning was used well. A Carrington-class event is not a standardized switch labeled global blackout. It is an extreme stress test applied to a system that is different from place to place. This is one reason claims about the exact consequences vary so widely. Some projections imagine very severe, long-duration outages if enough difficult-to-replace transformers are physically damaged. Other analyses emphasize that modern grids have protection, operating procedures, monitoring, and the ability to reduce exposure before the worst of the storm arrives. Both ideas can be true at once. The grid is vulnerable. The grid is also managed. A severe storm can create serious risk without guaranteeing the worst-case outcome. The Carrington event itself adds another layer of uncertainty because we do not know its exact intensity in the same way we would know a modern event. There were magnetic observatories in 1859, and some surviving records show extraordinary disturbances. The record from Colaba in Bombay became especially famous. Researchers have tried to translate those historical measurements into modern indices such as DST, which is used to describe large-scale geomagnetic storm intensity. One dramatic estimate produced a value around -1700 nanotesla. That number has been repeated widely because it is memorable and alarming, but it should not be treated as a direct modern measurement. DST is normally constructed from observations across multiple low-latitude stations. The 19th century network was sparse. The large change recorded at Bombay may have contained strong local effects that do not map cleanly onto the global quantity we would calculate today. Other reconstructions have suggested values closer to roughly -8 or 900 nanotesla. Still extreme, still far beyond an ordinary storm, but not the same number. This uncertainty is useful. It reminds us that Carrington is not a laboratory specimen. It is a historical event reconstructed from incomplete evidence. We have Carrington's solar observation. We have Hodgson's independent report. We have magnetic records. We have telegraph disturbances. We have auroral sightings. We have newspapers, letters, and other descriptions. From these pieces, scientists build a picture. The The picture is strong enough to show that the event was exceptional. It is not precise enough to give us every parameter we would like. And that means any statement beginning with, if the exact 1859 storm happened today, is already doing some reconstruction. We can explore plausible consequences. We cannot rerun the event with modern instruments. Another severe historical storm helps place Carrington in context. In May 1921, Earth experienced a major geomagnetic disturbance that again caused widespread trouble in telegraph and telephone systems. Electrical equipment sparked. Communication networks failed in places. Fires were associated with some signaling and communication facilities. The world had become more electrically connected since 1859, and the same broad natural mechanism found more opportunities to interfere. This is a pattern worth noticing. The sun did not need to change. Civilization changed beneath it. In 1859, the vulnerable network carried messages. By 1921, electrical communication and signaling had become far more deeply embedded in transportation and commerce. By 1989, the vulnerable network carried electrical power itself. Today, the grid supports almost everything else. That does not mean a power failure instantly destroys those other systems. Most critical systems have some form of backup, but backup introduces another clock. A hospital may switch to generators. A telecom site may run on batteries. A data center may have uninterruptible power supplies and backup generation. A water utility may have emergency power. A household may have a battery bank or generator. These systems do not remove the importance of the grid. They buy time. That distinction becomes central if the outage lasts. But before we follow the blackout into homes and hospitals, it is worth staying for a moment inside the control room. Because modern operators are not passive, if a significant geomagnetic storm is forecast, utilities can prepare. They can reduce loading on vulnerable parts of the network. They can postpone maintenance so important equipment remains available. They can adjust power flows. They can bring additional reactive power resources online. They can monitor geomagnetically induced currents. They can watch transformer temperatures and neutral currents. They can coordinate with neighbouring systems. They can place the grid in a less efficient but more resilient state. That last trade-off appears often in emergency planning. Efficiency is what you want on ordinary days. Margin is what you want during unusual ones. A system running near its optimum economic configuration may not be the system you want when the sun has just launched an enormous magnetized cloud toward Earth. So operators create room. They sacrifice some efficiency. They increase redundancy. They prepare for something that may not become as severe as forecast. And that creates another human problem. Overreaction is visible. Prevention is not. If a utility changes operations, restricts transfers, delays maintenance, or takes expensive precautions, and the storm passes without major damage, people may conclude that the warning was exaggerated. If operators do too little and serious damage follows, the same people ask why nobody prepared. This is not unique to space weather. Rare event management always works inside uncertainty. The best outcome is often one in which nothing dramatic happens. Nothing dramatic is difficult to prove. And there is no simple solution such as turning off the entire grid before impact. At first, that idea sounds attractive. If currents are entering long transmission systems, disconnect the system, protect the transformers, then switch everything back on later. Except large electrical grids are not household appliances. Shutting them down deliberately would itself create a massive emergency. Hospitals would move to backup power. Water systems would depend on generators. Traffic systems would fail. Businesses would close. Heating or cooling could become dangerous. Industrial processes might be damaged by uncontrolled shutdown. And restarting a large grid after widespread de-energization is complicated. Power plants themselves often require electrical power for pumps, controls, cooling, fuel handling, and auxiliary systems. Some generating units can start independently. These are known as black start resources. They can provide the first islands of electricity used to restore other generators and reconnect larger sections of the network. A large blackout is therefore not reversed by simply flipping the same switch back. Restoration is built. A generator starts. A line is energized. Another station comes online. Loads are added carefully. Frequency and voltage are controlled. Sections are synchronized. The grid returns piece by piece. This is one reason physical damage matters so much. If the system trips but major equipment survives, restoration can begin relatively quickly. If critical transformers are damaged, the problem becomes longer. Large, high-voltage transformers are not objects a utility can replace like light bulbs. They can be enormous, heavy, specialized. Some are designed for specific installations. Transport can require special trailers, route planning, bridge assessments, and sometimes unusual handling equipment. Manufacturing replacements can take time. Utilities maintain spares and participate in sharing arrangements because this vulnerability is well known. But enough simultaneous damage could still create serious delays. Again, the key word is enough. A Carrington-level storm does not automatically destroy every transformer. The frightening long-duration scenarios require significant physical damage across enough important equipment that restoration becomes constrained by replacement rather than switching and repair. That is possible. It is not inevitable. This distinction is what separates useful preparedness from apocalypse theatre. A realistic extreme event may be very serious without resembling the permanent end of electrical civilization. And if the grid begins failing during our hypothetical storm, the first experience for most people would be almost disappointingly ordinary. A light goes out. The room becomes quiet. For a second, nobody moves. That pause, after unexpected darkness, is familiar to almost everyone. You wait because most outages are temporary. Maybe a breaker has tripped. Maybe the neighborhood lost power. Someone checks the hallway. Dark. Someone looks out the window. The streetlights are off too. Phones come out. Screens illuminate faces. People open an outage map. If the network still works, they discover the affected area is larger than expected. A message goes to a friend. Is your power out? Yes. Another message travels farther. What about downtown? Yes. Then someone in another city answers that their lights are still on. The event becomes uneven. That unevenness matters. A severe geomagnetic storm would not necessarily darken every region at once. Some grids might remain stable. Others could experience localized problems. Some areas might lose power briefly. Others could suffer larger outages. Cloud cover might prevent people in the worst-hit region from seeing any aurora at all. Another city might have a magnificent sky and no serious power problem. This creates two contradictory public experiences. One person sees extraordinary aurora, keeps electricity, and decides the event was mostly beautiful. Another sits in a dark apartment and hears someone online say nothing serious is happening. Large, distributed disasters often produce this problem. Everyone sees one piece. Very few people see the whole system. And the grid itself may also fail in pieces. One section separates safely. Another remains connected. Operators shed load deliberately to prevent larger instability. A city may go dark not because every component inside it is damaged, but because removing load protects the wider network. This feels like failure from the street. From the control room, it may be damage prevention. The distinction matters later because a deliberately disconnected region can often be restored much faster than one filled with damaged equipment. But the person sitting in darkness does not experience the distinction. The refrigerator is silent either way. The air conditioner has stopped. The elevator does not respond. The home router is dark. Traffic signals outside may be out. A modern blackout is full of systems that are physically intact but temporarily useless. That is where the Carrington scenario becomes more interesting than a simple story about destroyed machines. Modern civilization depends heavily on access. A phone with no network, a bank account with no payment connection, fuel underground with no working pump, water in a reservoir with insufficient pumping, food inside a freezer with no electricity, a perfectly good elevator with no power. The objects remain, the service disappears. This creates a period in which the world looks almost normal. Buildings are still standing, roads are intact, cars are parked, stores contain goods. The physical landscape has not changed. Only the invisible systems organizing it have become uncertain. And for the first few hours, most of those systems have something left. Battery, fuel, pressure, stored cold, stored water, stored charge. Backup communication. The grid has failed, but the city has not. Not yet. The real question is how long those reserves can keep pretending that normal life is still there. The real question is how long those reserves can keep pretending that normal life is still there. For the first few minutes after a large blackout, surprisingly little may seem urgent. A laptop continues running on its battery. A phone remains charged. Emergency lights appear in hallways. Many buildings have backup systems. Mobile towers may still function. Hospitals transfer critical loads to emergency power. Water already stored in tanks and pipes does not immediately disappear. Refrigerators remain cold simply because insulated boxes take time to warm. The city has lost electricity, but it still contains yesterday's electricity in small pieces, stored in batteries, stored as pressure, stored as cold, stored as fuel. And for a while, those leftovers make the failure feel temporary. People reach instinctively for their phones. That small rectangle has become the first diagnostic instrument of modern inconvenience. Is it just this building? Is the neighborhood out? Did someone hit a utility pole? Is there an outage map? Has the power company posted anything? Messages begin moving between families. Do you have power? No. What about your area? No. The questions spread outward until someone realizes the outage is much larger than the room they are standing in. If mobile networks remain available, information can travel quickly. Emergency alerts can explain what is happening. Utilities can publish restoration estimates. Families can locate one another. Rumors can also move with extraordinary efficiency, because communications technology does not become wise merely because the situation is serious. A severe solar storm would be particularly good material for confusion. The cause is invisible. The terminology is unfamiliar. There may be spectacular auroras overhead. Scientists may use phrases such as geomagnetically induced current, coronal mass ejection, or southward interplanetary magnetic field, while most people want an answer to a much simpler question. When will the electricity come back? And during the first hour, that question may not have a reliable answer. Grid operators may still be determining what has tripped and what has been damaged. Some areas might be restored quickly, others may need inspection. If the geomagnetic disturbance is continuing, operators may hesitate to reconnect vulnerable equipment immediately. Restoring power while the storm is still strongly driving currents through the network could simply reproduce the problem. So darkness can become a form of protection. That is not especially comforting if you are inside it. At street level, the first changes are mundane. Traffic lights stop working. Where drivers remain calm, intersections become slow negotiations. Where they do not, the usual human experiment begins. A road designed around automatic signals suddenly depends on eye contact, patience, and the optimistic belief that everyone remembers whose turn it is. Subways and electrically powered rail systems may stop or reduce service depending on the outage and their backup arrangements. Some trains may be stranded until passengers can be moved safely. Electric doors and gates need alternative procedures. Office workers begin walking down staircases. In a 10-story building, this is inconvenient. In a 40-story building, it becomes exercise with consequences. For anyone with limited mobility, an elevator is not a convenience at all. It is access. The same outage can therefore mean mildly annoying stairs to one person and practical confinement to another. That difference is easy to miss when we talk about blackouts in terms of megawatts. Infrastructure failures are rarely equal experiences. Age matters. Health matters. Building design matters. Weather matters. Money matters. Location matters. A person in a detached house with stored water, a generator, and a full fuel tank experiences a different event from someone on the 30th floor of a tower. The electrical failure may be identical. The human failure is not. Weather would shape almost everything that follows. A major outage during mild spring weather could remain manageable for many people for quite some time. The same outage during severe heat becomes more dangerous. Air conditioning stops. Apartments begin warming. Buildings designed to remain sealed and mechanically cooled can become uncomfortable surprisingly quickly. Windows that barely open, excellent when the climate system works, become less impressive when it does not. At night, sleep becomes difficult. People move toward balconies, courtyards, shaded areas, or any place with airflow. Older adults, infants, and people with certain health conditions become more vulnerable to heat stress. During extreme cold, the problem reverses. Electric heating fails immediately. Gas heating may also fail if furnaces require electrical controls, fans, pumps, or ignition. Indoor temperatures begin dropping. Pipes become vulnerable. Families close doors to unused rooms and gather in smaller spaces. The architecture of comfort becomes architecture of heat retention. Again, the solar storm itself is not what hurts people. The storm interrupts electricity. The absence of electricity allows weather to become more important. Modern buildings have not defeated climate. They have installed machinery between us and it. Water introduces another clock. When the electricity disappears, water does not necessarily stop at once. Municipal systems often have storage reservoirs, elevated tanks, gravity-fed portions, emergency generation, or enough existing pressure to continue service temporarily. That delay can create another false sense that the outage is mostly an inconvenience. The tap works, so things cannot be too bad. But many water systems depend heavily on electrical pumps. Water has to be treated, moved, pressurized, lifted. Wastewater must also be transported and processed. High-rise buildings may require pumps to move water to upper floors, even when municipal supply remains available at street level. A person on a lower floor might still have running water, while someone much higher in the same building does not. That is the peculiar geography of a blackout. A few dozen meters of height can become a meaningful difference. If an outage continues, authorities may ask residents to conserve water. Pressure may fall. Some areas may face boil water advisories if treatment or distribution integrity becomes uncertain. Wastewater systems can become another concern if pumping stations lose power for longer than their backup arrangements can support. These are not inevitable consequences of every blackout. They depend on the system, its design, backup power, and duration. But they show why the length of an outage matters more than the initial drama. A city can tolerate many failures briefly. It tolerates fewer of them indefinitely. Food behaves the same way. The moment the power goes out, people think about the refrigerator, usually too soon. A closed refrigerator can keep food safely cold for a limited period, and a full freezer can retain low temperatures considerably longer if the door remains shut. The sensible action is almost comically difficult. Do nothing. Do not keep opening the door to check whether it is still cold. The refrigerator is now an insulated container. Every inspection exchanges cold air for warm air. So families begin negotiating with an appliance. What do we need? Get it quickly. Close the door. Do not open it again. After enough hours, the calculation changes. Which food will spoil first? What can be cooked? What can be shared? What should be thrown away? A long outage can produce the odd sight of people eating unusually well at exactly the moment they are becoming worried about food. Frozen meat comes out. Ice cream becomes urgent. Expensive ingredients saved for later suddenly have a deadline. The freezer begins dictating the menu. There is a small historical irony in this. For most of human history, preserving food required constant attention. Drying, salting, smoking, fermenting, cooling in cellars, eating seasonally. Modern refrigeration removed much of that daily anxiety. Then, during a prolonged outage, the old problem returns inside a very modern kitchen. Food is available. Time is eating it. Supermarkets face the same problem on a larger scale. A grocery store contains enormous quantities of food, but much of its operation depends on electricity, lighting, refrigeration, freezers, inventory systems, electronic payment, automatic doors, security, communication, warehouse coordination. The building may contain everything people need while losing some of the systems needed to distribute it normally. Backup generation can keep parts of a store operating, but arrangements vary. If power loss becomes widespread, demand changes immediately. People do not shop as they normally would. They buy the things they fear will become unavailable. Water, shelf-stable food, batteries, flashlights, ice, fuel, cash, if they can get it. The behavior is individually sensible. Collectively, it can empty shelves very quickly. This is one of the recurring contradictions of emergency behavior. A shortage can begin before the underlying supply is actually exhausted. Expectation creates demand. Demand creates visible scarcity. Visible scarcity increases expectation. Then, someone photographs an empty shelf. The photograph travels. More people leave home to buy the same thing. Modern communication can therefore make a physical shortage worse while simultaneously helping people understand the emergency. Technology is rarely polite enough to have only one effect. Payment creates another problem. A person may have money. The shop may have food. Both parties may want the transaction, and the transaction can still fail because the electronic systems connecting them are unavailable. Card terminals require power and communications. Banks depend on data networks. ATMs require electricity, connectivity, and eventually physical cash replenishment. Mobile payment depends on multiple layers of functioning infrastructure. Even if the wider financial system remains completely solvent, local access can become unreliable. This is why modest amounts of physical cash still appear in practical emergency guidance. Not because a solar storm is expected to destroy money, because the representation of money and the ability to use money are different things. Your bank balance can survive perfectly well in a data center while being temporarily useless at a dark cash register. The 19th century person would find this arrangement fascinating. We have made money much easier to move by making it increasingly dependent on electricity. That is a very reasonable trade most days. Emergency planning is largely the study of what happens on the other days. Fuel is even more physical. Petrol and diesel can be sitting underground at a service station. The fuel exists, the car exists, the driver has money, but pumps require electricity. Payment systems require electricity and communications. Stations with backup generation may continue operating, others may not. Then, queues form around the stations that can still pump. Those queues consume fuel while people wait for fuel. Again, civilization produces small jokes at inconvenient times. Fuel matters for more than private cars. Emergency generators need it. Hospitals may need it. Telecommunications sites may need it. Water utilities may need it. Emergency services need it. Repair crews need it. Warehouses and transport fleets need it. If the grid outage becomes prolonged, fuel distribution itself becomes part of restoration. Tankers have to reach the places where backup systems are operating. Roads need to remain passable. Terminals need to function. Drivers need instructions. Deliveries need prioritization. A generator is not an independent power source forever. It is a machine attached to a fuel supply chain. The same is true of batteries. They are excellent bridges. They are not permanent islands. Telecommunications illustrate this very clearly. When the power first fails, a mobile phone may work perfectly. Cell towers and network equipment often have batteries or generators. The user may not notice any interruption. Then the network becomes crowded. Everyone begins calling and messaging at once. Capacity becomes strained. Some sites lose their normal grid connection. Batteries begin discharging. Generators start where available. A few sites fail. Traffic shifts to surviving sites. Those become more heavily loaded. Coverage develops gaps. A phone that showed full signal earlier may now show 1 bar, then none. The device itself can be completely healthy. It simply has nothing nearby to speak to. People adapt quickly. They turn off unnecessary functions. Lower screen brightness. Use airplane mode between checks. Search for charging stations. Charge from cars if possible. Portable battery packs become suddenly important. A household that has spent years arguing over missing phone chargers may discover that the missing charger was apparently a strategic national resource after all. But the deeper change is psychological. When communication works, distance feels small. A relative across a city can be reached instantly. When communication becomes unreliable, geography returns. You begin thinking in physical distance again. How far away are they? Could I walk there? Which roads are open? Did they receive my last message? Should I conserve the battery or keep trying? A failed message can create more anxiety than a failed light bulb because it leaves another person unresolved. During a large disruption, one successful text saying "I'm okay" can carry extraordinary emotional weight. This is why emergency communication systems often prioritize short, efficient information. Text messages may succeed when voice networks are congested. Radio remains valuable because one transmitter can reach large numbers of receivers without each listener needing a separate two-way connection. An old battery-powered radio can look almost absurdly primitive beside a smartphone. Then the smartphone loses its network. The radio keeps talking. Technological progress does not always eliminate old tools. Sometimes it gives them retirement jobs. Hospitals have much more elaborate layers of protection. Critical medical facilities plan for grid failure precisely because ordinary power outages already happen. Emergency generators can start rapidly. Uninterruptible power supplies can bridge the transition for sensitive equipment. Critical circuits are prioritized. Operating rooms, intensive care units, emergency departments, medical devices, communications, refrigeration for medicines, and other essential systems may be supported according to the facility's design. So, a citywide blackout does not mean every hospital suddenly goes dark, but hospitals become more vulnerable as time passes. Generators require fuel. Generators can fail. Some building systems may not be on emergency circuits. Cooling becomes important. Water matters. Staff have to reach the hospital. Supplies have to arrive. Pharmacies depend on distribution. Patients who normally receive care elsewhere may begin arriving because their own home equipment or local facilities no longer function. The hospital becomes a functioning island inside a less functional city, and islands receive visitors. Emergency departments may see people with injuries from dark streets, heat or cold exposure, generator misuse, medication problems, and the ordinary accidents that become harder to manage when infrastructure is disrupted. Home medical equipment creates a particularly personal vulnerability. Oxygen concentrators, powered mobility devices, home dialysis equipment in some circumstances, refrigerated medicines, communication devices. Battery-powered monitors. Again, the danger is not uniform. Most households can tolerate several hours without electricity with annoyance. Some cannot. Emergency planning, therefore, becomes partly a matter of identifying who runs out of time first. A healthy adult with water, food, and mild weather may have a generous margin. Someone dependent on powered medical equipment may have a much shorter one. A nursing facility may have another. A telecom battery another. A supermarket freezer another. A water pump another. The city after a blackout is full of clocks. Most of them are invisible, and they are all counting down at different speeds. That is why the phrase, "the power is out," describes only the beginning. The blackout itself is one event. What follows is thousands of systems consuming whatever resilience they had stored beforehand. For a few hours, those reserves overlap. The city continues functioning surprisingly well. Then some begin expiring, and when one system fails, it can shorten the clock of another. If telecommunications weaken, coordinating fuel deliveries becomes harder. If fuel becomes difficult to distribute, generators become less dependable. If transport is disrupted, repair crews and medical staff move more slowly. If electronic payments fail, ordinary purchasing becomes more difficult. If water systems become strained, hospitals and households face additional problems. This is the beginning of a cascade. Not a cinematic cascade where everything collapses simultaneously. A slow one, uneven, annoying before frightening. One neighborhood has water, another has low pressure. One supermarket opens using emergency power, another remains closed. One mobile network works intermittently, another performs better. One hospital is comfortable, another begins conserving generator fuel. One family has a charged battery bank. The family next door has 3% left on a phone and no idea where they put the flashlight. The differences become more visible after dark. During daylight, a powerless city can still resemble itself. People move, cars travel, buildings stand, stores may open manually, windows provide light. Then the sun sets. The scale becomes visible. A normal city at night is an enormous display of electrical confidence. Streetlights, apartments, offices, signs, parking garages, traffic signals, stations, shop windows, towers. All of it quietly announces that energy is available. When those lights disappear across a large area, the city changes shape. Familiar streets become harder to recognize. Intersections become darker than expected. Buildings lose their visual boundaries. The skyline becomes a silhouette, and above it, if the geomagnetic storm is still active and the sky is clear, there may be something modern city dwellers almost never see. Stars, possibly thousands more than they are accustomed to. And beyond them, the aurora. Red curtains may stretch across a sky that is suddenly free of urban glare. Green structures may move closer to the horizon. The same storm responsible for some of the darkness could make the heavens unusually bright. That would be a difficult sight to interpret emotionally. Beautiful is not quite enough. Frightening is not quite right either. People would photograph it if their batteries allowed. Some would stand outside simply because apartments had become hot and dark. Children might be delighted. Adults might be less certain. Somewhere, engineers would still be working. Somewhere, crews would be driving towards substations. Somewhere, operators would be waiting for magnetic conditions to improve enough to restore another section safely. And most people would be doing something far less dramatic. Waiting. Blackouts contain enormous amounts of waiting. Waiting for an update. Waiting for a signal. Waiting for the lights. Waiting in a fuel queue. Waiting for an elevator that is not coming. Waiting to hear from someone. Waiting for the tap pressure to return. Waiting for the refrigerator to become a refrigerator again. Time changes slightly when the machines that normally organize it stop. There is less to do after dark. There are fewer places to go. The battery percentage becomes a clock. Sunset becomes important. Morning becomes useful. Meals become decisions. Neighbors become more relevant. And this last change is one of the more consistent features of real disasters. People do not automatically become violent the moment infrastructure fails. Popular disaster fiction enjoys that idea because orderly cooperation is apparently not exciting enough. Actual human behavior is more complicated. There can be theft, there can be conflict, there can be exploitation, but disasters also repeatedly produce spontaneous cooperation. People share information, check on neighbours, direct traffic, offer charging, move food before it spoils, help older residents downstairs, share generators, cook together, provide rides. A building full of people who previously exchanged little more than polite greetings can suddenly develop a small information network in the lobby. Who has water? Which shop is open? Has anyone heard when power returns? Does the woman in apartment 14 need help? Who has a radio? This is not sentimental. Cooperation is practical. When formal systems weaken, nearby humans become infrastructure. The neighbour with a working car becomes transport. The person with a battery radio becomes information. Someone with a camping stove becomes a kitchen. Someone who knows first aid becomes more valuable than they were yesterday. The social network becomes literal again. This does not mean everyone behaves beautifully. Fear can make people selfish. Scarcity can produce conflict. Rumours can cause dangerous behaviour. But the assumption that social order immediately disappears is not supported by the broader history of disasters. Often, people become more cooperative before they become less. The more serious danger is duration. If supplies remain limited for days rather than hours, patience becomes harder. If official information is absent, rumours become stronger. If some neighbourhoods receive help while others do not, resentment grows. If temperatures become dangerous, health problems accumulate. If businesses remain closed, livelihoods are affected. If schools cannot operate, families have new problems. If fuel is scarce, movement contracts. The crisis changes character. The first night is an outage. The third or fourth day in a severely affected region can become a logistics problem. And logistics is where modern civilization is both astonishingly capable and unexpectedly delicate. A supermarket does not normally keep months of food in the back room. A pharmacy does not manufacture medicine behind the counter. A city does not store everything it consumes inside its boundaries. Modern systems work through flow. Trucks arrive. Warehouses replenish. Fuel moves. Parts move. Medicine moves. Food moves. Information tells those things where to go. Electricity keeps the process synchronized. This is enormously efficient. It is one reason modern cities can support populations that would have been impossible under older systems of local production. But efficiency reduces the amount of unused material sitting around waiting for an emergency. The system expects tomorrow's delivery to arrive tomorrow. If tomorrow stops behaving normally, inventories begin to matter. This is where the more extreme Carrington scenarios become genuinely serious. Not because a solar storm somehow destroys food. Not because the sun empties reservoirs. Not because satellites fall onto cities. But because prolonged electrical disruption can interfere with the movement that keeps densely populated places supplied, and even here, the scale would depend enormously on the damage. If most major equipment survives and grid restoration proceeds steadily, the cascade may remain limited. Power returns to one area, then another. Telecommunications recover. Pumps restart. Fuel stations reopen. Stores reconnect. The system begins repairing itself faster than reserves are exhausted. But if significant grid equipment has been physically damaged across a wide region, recovery becomes slower. Then the problem moves away from the sky. The solar storm may already be weakening. Auroras retreat. Geomagnetic indices begin settling. The sun has finished the dramatic part. On Earth, the consequences may only now be becoming complicated. That distinction is important. A geomagnetic storm lasts for a limited time. An infrastructure failure can outlive its cause. The hurricane moves inland and weakens, but flooded roads remain. The earthquake ends, but damaged buildings remain. The solar wind changes, but a damaged transformer does not repair itself because the aurora has disappeared. Eventually, though, even the largest blackout becomes a restoration project. Crews inspect. Operators isolate faults. Equipment is tested. Power plants restart. Transmission paths are rebuilt. Electricity returns in islands. Those islands expand, and when a neighborhood finally reconnects, recovery announces itself through extraordinarily small sounds. An air conditioner starts. A hallway light appears. A router begins blinking. A refrigerator compressor comes back to life. Someone hears an elevator move. Phones begin charging. Water pumps start. Traffic lights wake. People cheer sometimes. Other people simply continue what they were doing. The miracle becomes ordinary again, almost immediately. But before we allow the lights to return completely, there is one part of the Carrington question still unresolved. We have followed the storm through the electrical grid and into the systems beneath ordinary life. Yet modern civilization contains another network, one even more difficult to see. It crosses oceans. It links banks, governments, businesses, homes, hospitals, markets, and machines. And it is often described as though it floats somewhere above the physical world. The cloud, the internet, the digital layer of civilization. If the electricity beneath it begins to fail, the question is not whether the sun can somehow burn the internet out of the air. It cannot. The question is much more practical. How long can a global network remain global when the physical machines underneath it begin losing power? How long can a global network remain global when the physical machines underneath it begin losing power? The answer begins with an inconvenient fact about the internet. It is much heavier than it sounds. We talk about the cloud as though our photographs, bank records, messages, films, business documents, and increasingly large portions of ordinary life have somehow floated away from the physical world. They have not. The cloud has flaws. It has walls. It has cables. It has cooling systems. It has electrical substations. It has backup generators and batteries. It occupies buildings that consume substantial amounts of power and produce substantial amounts of heat. The internet itself is distributed across an enormous collection of physical infrastructure: data centers, routers, switches, terrestrial fiber networks, cable landing stations, mobile networks, satellites, and undersea cables crossing the oceans. The useful thing about this arrangement is that there is no single machine called the internet. There is no central box somewhere that can be struck by a solar storm and switched off. The network was built to route around many kinds of failure. If one path becomes unavailable, traffic may move through another. If a server fails, another may answer. Important data may exist in several places. Large providers operate infrastructure across multiple regions. Network operators spend a great deal of time preparing for the deeply unromantic fact that machines break. This gives the internet considerable resilience. It also makes the phrase, "the internet goes down," less precise than it appears. For one person, the internet can disappear because the router in the living room has lost power. For an entire neighborhood, it may disappear because local telecommunications equipment has failed. A city can lose connectivity while the wider global network continues normally. A country can experience routing problems without the physical internet having been destroyed. The difference between the internet existing and you being able to reach it becomes important during a large blackout. At home, the failure may be immediate. The power disappears. The Wi-Fi router disappears with it. The fiber or cable entering the building may still be perfectly functional, but the small box converting that connection into something useful is dark. A battery backup can keep it running for a while. Most households do not have one. So a person reaches for the mobile phone. For the first hour, that may solve the problem. Then the cellular network begins experiencing the same pressures we saw earlier. Backup batteries are discharging. Generators are running where available. Traffic is unusually heavy. Some sites fail. Others remain operational. The network develops holes. The internet is still there. Access to it is becoming uneven. This distinction gets lost in some of the more dramatic claims about solar storms. One recurring idea is that a Carrington-level event could simply destroy the global internet, sometimes for months. There are legitimate reasons to study severe space weather as a threat to communication infrastructure. But the physical mechanisms matter. Fiber optic cable itself carries information as light through glass. Glass fiber is not a long copper telegraph wire waiting to collect geomagnetically induced current in the same way. That makes the optical fiber itself comparatively resistant to the direct induction problem that affected 19th century telegraph lines. The vulnerable parts are elsewhere: power supplies, electronic equipment, repeaters, routers, landing stations, terrestrial electrical connections, and the larger power systems that keep all of them operating. Undersea cables make this particularly interesting. Most international internet traffic does not cross oceans through satellites. It travels through cables lying on or beneath the sea floor. Those cables are among the most important pieces of infrastructure most people will never see. A cable may leave a coastal landing station, disappear beneath the ocean, and emerge thousands of kilometers away, carrying enormous quantities of data between continents. Because light signals weaken over distance, long submarine cables contain repeaters placed along the route to amplify the optical signal. Those repeaters require power. The power is supplied electrically through conductive components running along the cable system from shore-based equipment. This creates a possible interaction with geomagnetic disturbances. Researchers have examined whether extreme storms could produce problematic voltages in long submarine cable systems, particularly through their power feeding arrangements and grounded endpoints. There is reason to take that possibility seriously. There is not good reason to simplify it into a claim that a solar storm will burn every undersea internet cable. The systems are engineered. Different cable designs behave differently. Protection exists. And even the loss of some routes would not necessarily isolate entire continents, because the global network contains redundancy. The interesting failure would probably be less theatrical. A route goes down, traffic moves elsewhere. The remaining routes become more congested. Latency rises. Some services become unreliable. Operators work to understand which failures are electrical, which are local power problems, and which are network consequences. To a user, the result might be a website that will not load. The physical cause could be on another continent. That is the peculiar intimacy of global infrastructure. A failure thousands of kilometers away can arrive as a spinning symbol on your screen. Data centers face a more familiar problem. They need electricity continuously. Many large facilities have extensive backup systems. Batteries or uninterruptible power supplies bridge short interruptions. Generators can provide longer duration power. Fuel is stored. Redundant feeds may be available. Some facilities are designed to tolerate substantial failures without interrupting service. This is why an ordinary local blackout does not usually erase the internet. The data center simply keeps operating. But again, backup power introduces a clock. Fuel must be replenished if the outage continues. Cooling must remain functional. Network connections must survive. Staff must be able to reach the site. Parts must be available. The data center is resilient because many supporting systems have been duplicated. It is not independent of the physical world, and cooling deserves more attention than it normally receives. Computers turn electricity into computation and heat. A large concentration of servers produces a great deal of heat. Removing that heat is part of keeping the machines alive. If power supply becomes constrained, operators do not only ask whether there is enough electricity to run the processors, they ask whether there is enough to run the environment around them: cooling, pumps, fans, controls. Network equipment, security, a building full of perfectly functional servers can become unusable if the supporting systems cannot maintain safe operating conditions. Again, the pattern is familiar. The object survives. Access to its function does not. If our hypothetical storm produced severe but geographically uneven grid failures, the digital world might fragment in equally uneven ways. A data center in one region stays online, another transfers load, a third runs on generators. A mobile network continues in one city and becomes unreliable in another. A bank's central systems remain operational, but some customers cannot reach them. A streaming service works perfectly in one country and poorly in another. The experience would not necessarily resemble a single global switch being thrown. It might resemble the internet becoming less dependable, and dependence on reliability is one of the defining features of modern life. We do not merely use digital systems when they are convenient. We organize other systems around the assumption that they will be available. A restaurant may not keep paper copies of every transaction because there is no reason to. A delivery driver may not carry detailed printed maps. A traveler may not know the phone number of the hotel. A business may use cloud-based inventory. A warehouse may rely on networked scheduling. A pharmacy may depend on digital systems for records and prescriptions. A bank may require communication with remote systems before authorizing transactions. The loss of connectivity therefore creates work even when nothing has been physically destroyed. People begin reconstructing older procedures. Paper appears. Names are written down. Transactions are delayed. Instructions are given verbally. Someone prints something if the printer has power. A clipboard, having waited patiently for several decades, enjoys a modest professional revival. The systems that can degrade gracefully tend to perform better. This phrase, graceful degradation, is not especially poetic, but it describes an important property of resilience. A robust system does not have only two states, perfect and useless. It can become less capable without becoming completely non-functional. A hospital may lose some administrative systems while maintaining critical care. A telecommunications network may prioritize emergency traffic. A power grid may shed some load to preserve the remainder. An aircraft can use alternative navigation procedures. A shop can accept cash. A person can use a paper map. The ability to become temporarily worse is often what prevents a system from becoming entirely unavailable. Modern efficiency sometimes works against this. If every process is optimized around one digital path, losing that path creates a larger problem. Redundancy can look wasteful until the primary system fails. Then the waste acquires a new name, preparedness. GPS gives us an especially clear example. The Global Positioning System is commonly thought of as a navigation service. It is much more than that. GPS satellites carry extremely accurate atomic clocks. Receivers use the timing of signals from multiple satellites to determine position. But that precise timing is also used throughout modern infrastructure. Telecommunications networks use satellite-derived timing. Financial systems can use accurate timestamps. Power systems use synchronized measurements. Scientific instruments depend on precise time. Other global navigation satellite systems provide similar services. We have quietly placed a network of clocks in orbit and built terrestrial systems around their reliability. Geomagnetic and ionospheric disturbances can degrade satellite navigation. The signal from a navigation satellite is weak by the time it reaches the ground. It passes through the ionosphere, a region whose electron density changes during space weather events. Those changes can alter the signal path and introduce positioning errors. During strong disturbances, receivers can lose accuracy or even lose track of signals temporarily. This does not mean every GPS receiver stops working. Effects vary by location, equipment, frequency, and conditions. But again, accuracy matters differently to different users. A person walking toward a restaurant may tolerate an error. A precision agricultural system may not. Surveying may not. Certain aviation procedures may not. Marine operations may not. Timing applications may have their own tolerances and backups. This is why the same storm can be a curiosity for one person and an operational problem for another. In May 2024, farmers provided an unusually understandable demonstration. Some precision agricultural systems experienced disruption during the geomagnetic storm. The tractor engine did not fail. The field did not become dangerous. The problem was position. Planting equipment that depends on high precision guidance can become difficult to use when that precision deteriorates. There is something wonderfully strange about the chain of dependence. A farmer sits in a machine on soil. The task is ancient. Put seed into ground, but the modern version may depend on radio signals from atomic clocks thousands of kilometers overhead. Disturb the ionosphere, and a row of crops can become crooked. Civilization has become extremely good at hiding complexity inside ordinary actions. Paying for coffee can involve data centers. Driving can involve satellites. Opening a tap can involve electrical pumps. Calling your mother can involve fiber beneath an ocean. The actions remain simple because the infrastructure is complicated. Space weather reveals the complication. Satellites themselves face more direct hazards. Energetic particles can interfere with electronics. Electrical charging can build on spacecraft surfaces or within components. Sensors can produce false readings. Computers can experience errors. Operators may temporarily place satellites into safer configurations. During strong geomagnetic storms, the upper atmosphere heats and expands, increasing drag on spacecraft in low Earth orbit. We have already seen how this can change orbits. For a single satellite, operators may compensate. For a large constellation containing thousands of spacecraft, even small orbital changes become an enormous tracking problem. After the May 2024 storm, satellite operators had to deal with widespread changes in orbital drag. The sky above us has become an active infrastructure zone. This creates a subtle, modern vulnerability. Space is no longer merely where scientific instruments go. It contains systems tied to communication, navigation, weather forecasting, agriculture, mapping, finance, national security, and everyday consumer services. A solar storm does not need to destroy those satellites to create difficulty. It only needs to make enough of them unreliable at the same time. That phrase returns repeatedly. At the same time, a broken machine is a maintenance problem. Many stressed systems together become an emergency. The same is true of aviation. Commercial aircraft do not depend on one navigation signal or one communication method for every situation. There are layers of systems and procedures. But solar activity can interfere with high-frequency radio, especially on polar routes, while energetic particle conditions can increase radiation exposure at high altitude. Airlines can respond by rerouting flights. This costs time and fuel. It may create delays. Passengers may miss connections. Crews may reach duty limits. One altered route produces consequences elsewhere in the schedule. Again, a solar storm can reach someone without that person ever seeing an aurora. They simply arrive 4 hours late and spend those 4 hours blaming the airline. The airline, in this case, may have the unusual defense that the sun was involved. For the modern Carrington scenario, this scattered pattern matters. We tend to imagine catastrophe spatially. A city burns. A coastline floods. A building collapses. The damage is visible in one place. Extreme space weather is different. Its effects can be geographically enormous while remaining strangely selective. A transformer is stressed in one region. A satellite has an anomaly over another. Radio communication degrades across a polar route. GPS accuracy worsens across agricultural areas. A data center changes to backup power because the local grid has failed. A submarine cable landing station operates normally while another faces power trouble. Millions of people see aurora and experience nothing more serious than a beautiful night. Others, beneath the same storm, encounter genuine disruption. This makes the event difficult to describe while it is happening. Is it catastrophic? Not everywhere. Is it harmless? Not everywhere. And the internet would magnify that disagreement. Someone with power posts a photograph of the aurora and jokes about the apocalypse that failed to arrive. Someone several hundred kilometers away is sitting in a dark building with no mobile service. Both are accurately describing their own night. This is why extreme event communication is difficult. People trust direct experience. If the warning says severe storm and nothing happens to you, the warning can feel excessive. If the warning says conditions are manageable and your local system fails, it can feel dishonest. But risk is not a promise about what will happen to every person. It is a description of what may happen across a system. The Carrington event itself teaches this lesson. Not every telegraph line behaved identically. Not every location saw the same aurora. Not every observer described the same color or brightness. The event was planetary. The experience was local. A modern version would be the same, only multiplied across far more technologies. And eventually, if the electrical failures were severe enough, another modern assumption would begin to weaken. We are accustomed to knowing what is happening. During almost any event today, information appears immediately. Maps update. News arrives. Friends post photographs. Official agencies publish warnings. Flights can be tracked. Power outages can be mapped. Weather can be watched in real time. The world feels observable. A widespread disruption to power and communications would damage not only the systems themselves, but our ability to see the damage. An outage map is useful only if the servers, communications, and user's device can reach one another. A family tracking application is useful only if both phones can communicate. A digital news service is useful only if the audience has power and connectivity. At some point, information becomes patchy. And when reliable information becomes patchy, rumors fill the gaps. This may be one of the most psychologically difficult parts of a prolonged technological disruption. Uncertainty becomes personal. Has the hospital got power? Is the water safe? Is the fuel station open? Is the outage expected to last hours or days? Is the mobile network down because of congestion or because equipment has failed? Did that message from a relative fail to send or fail to arrive? Is the alarming post circulating online current, or is it a photograph from another country, another year, another storm entirely? During the first hours, authorities would try to maintain communication through multiple channels. Emergency radio, broadcast television, where power remains available, mobile alerts, web services, local announcements, satellite communication, public safety networks. The more redundant these channels are, the better. And once again, an older technology can become unexpectedly useful. Radio broadcasting requires a transmitter and receivers. Millions of listeners do not each need a separate connection to the broadcaster. A battery-powered radio can receive information while using very little energy. It does one thing. In an emergency, doing one thing reliably is an underrated talent. As communications become less dependable, physical distance becomes larger again. The friend who normally exists one instant away through a messaging app may now be 20 kilometers away. A parent across town is no longer a notification. They are a journey. People begin making decisions based on geography. Should I stay here or try to reach them? Are the roads safe? Do I have enough fuel? Will the network return if I wait? Will they come looking for me if I leave? This is where the digital failure becomes a human one. Not because people cannot watch videos, because coordination becomes harder. Modern cities function through coordination. Ambulances are dispatched. Deliveries are routed. Repair crews receive assignments. Hospitals share information. Warehouses track inventory. Utilities communicate with field teams. Transport systems adjust. Governments distribute instructions. Businesses coordinate staff. Families coordinate themselves. The internet is valuable not merely because it contains information, it allows millions of decisions to be synchronized. If connectivity becomes degraded, those decisions slow down. People compensate. Radios, local networks, dedicated emergency communications, satellite links, paper, runners in extreme cases, face-to-face coordination. None of these are as efficient as the normal network. They do not need to be. They only need to preserve the most important functions until normal systems return. And this is where the apocalyptic version of the Carrington story begins to lose some of its power. Modern civilization is extraordinarily dependent on electricity and communication. That dependence is real. But dependence is not the same thing as having no resilience. The same complexity that creates vulnerability also creates alternatives. There are multiple electrical regions, multiple communication providers, multiple data centers, multiple submarine cables, multiple satellite systems, emergency generators, batteries, spare equipment, black start generators, mutual assistance agreements, emergency management agencies, engineers whose entire professional purpose is to think about failures before they happen. None of these guarantees safety. But neither does a severe storm arrive against a civilization that has never experienced a blackout. The more useful question is not whether modern society can fail. It can. The useful question is where recovery becomes difficult. And one answer is beginning to appear. The deepest danger is not the first failed device. It is the loss of enough connections between systems that each system can no longer help restore the others. Electricity supports communications. Communications coordinate fuel. Fuel supports generators. Generators support water and hospitals. Transport moves repair crews. Digital networks coordinate transport. Each supports another. During a cascade, those dependencies can pull downward. During recovery, they can also pull upward. Restore electricity to a telecommunications site, and communication improves. Communication improves fuel delivery. Fuel keeps generators operating. Working communications and transport help utility crews restore more electricity. The same network that makes failure complicated can make recovery accelerate. That is why the length of the crisis depends so heavily on physical damage. If equipment has mostly protected itself by disconnecting, reconnection can begin. If enough major equipment has been destroyed, the climb becomes slower. And this brings us back to one of the most frightening claims attached to the Carrington event. The idea that a future solar superstorm could leave entire regions without electricity for months, perhaps even years. There are scenarios in which long-duration disruption is a legitimate concern. Large transformers are difficult to replace. Manufacturing capacity is finite. Transporting them can be complicated. Simultaneous damage would strain inventories. But the phrase "years without electricity" often escapes from those conditional scenarios and becomes something much simpler. A prediction. It is not a prediction. Neither is the opposite claim that modern grids would certainly handle a Carrington-level storm without major difficulty. We do not know. The storm itself cannot be specified exactly. The grid is constantly changing. Protection improves. Vulnerabilities change. Renewable generation, power electronics, storage, distributed generation, and new transmission infrastructure alter the system in ways that can create both strengths and complications. A future Carrington event would therefore be an experiment we would strongly prefer not to conduct. But we are not completely blind about the result. We have historical storms. We have modern storms. We have simulations. We have measurements. We have engineering studies. We have 1989. We have 2003. We have 2012, when the powerful eruption missed Earth. We have 2024, when an extreme category geomagnetic storm arrived and the modern world remained overwhelmingly functional. Each event gives another piece of the answer, and the answer emerging from them is neither comforting enough for complacency nor dramatic enough for apocalypse. A truly extreme storm could cause serious disruption. Some regions could fare much worse than others. Certain satellites and communications could experience significant problems. Power grids could face severe stress. Under difficult conditions, physical equipment could be damaged, and outages could last much longer than ordinary blackouts. Secondary failures could affect water, fuel, food distribution, healthcare, and communications. But there is no credible mechanism by which the sun simply erases every computer, destroys every car, burns every cable, disables every phone, and sends the entire planet permanently backward into a pre-industrial age. The modern world is vulnerable in much more interesting ways than that. It is vulnerable through dependencies, through timing, through geography, through bottlenecks, through equipment that is difficult to replace, through people assuming another system will always be available. And because those vulnerabilities can be identified, many of them can also be reduced. That changes the final part of our story. So far, humanity has mostly been reacting. Carrington watched. Telegraph operators improvised. Engineers studied later storms. Quebec went dark. Satellite operators learned. Grid operators changed procedures. But today, for the first time in this story, we can move ahead of the storm. We can watch the sun before the sky turns red. We can estimate what is coming. We can deliberately make systems less vulnerable. And we can prepare ordinary people without asking them to build a bunker, abandon technology, or spend the rest of their lives nervously checking sunspots. The question is no longer only what the sun can do to us. It is what we have learned to do before it arrives. The question is no longer only what the sun can do to us. It is what we have learned to do before it arrives. That difference separates our world from Carrington's more than any particular transformer, satellite, or computer. In 1859, the warning and the event were almost the same thing. Carrington saw the sudden brightening on the sun, recorded it carefully, and had no practical reason to imagine that people operating telegraph equipment across the world should immediately begin preparing for what he had observed. The connection between solar activity and geomagnetic disturbance was still being assembled from scattered evidence. Today, an eruption begins a sequence of observation. The sun is watched continuously from space and from the ground. Active regions are tracked as they rotate across the solar surface. Instruments detect the sudden radiation from powerful flares. Other instruments observe material expanding outward through the corona. When a large coronal mass ejection appears to be traveling toward Earth, forecasters begin estimating its speed and likely arrival. There is something quietly remarkable about this. The object threatening modern technology may be moving through space at well over 1 million kilometers per hour, yet humans can see it leave. We can watch the beginning of the journey. We can calculate where Earth will be, and then, in many cases, we wait. For an ordinary person, that waiting might begin with a notification. A strong solar flare has occurred. An Earth-directed CME may arrive tomorrow. The language would probably sound more dramatic than the immediate experience. The lights would still be on. The phone delivering the warning would still be connected to a network. Shops would remain open. Aircraft would cross oceans. Trains would move. Water would come from taps. Nothing in the room would provide evidence that an enormous cloud of magnetized plasma was traveling toward the planet. This is one of the unusual advantages of space weather compared with many terrestrial hazards. An earthquake can arrive before a meaningful warning is possible. A tornado may offer minutes. A hurricane can provide days, but its path can shift and its local consequences depend heavily on geography. A major coronal mass ejection can sometimes give us many hours of notice that something is approaching. That does not mean we know exactly what it will do. The warning comes in layers. The first layer tells us that the sun has produced something large. The next tells us whether it appears to be heading toward Earth. Its observed speed gives a rough sense of when it may arrive. Models refine that estimate, but one of the most important pieces of information remains frustratingly difficult to know from a distance: the magnetic orientation carried inside the approaching plasma. We encountered this earlier because it is central to the entire problem. If the magnetic field within the incoming material is oriented in a way that couples strongly with Earth's magnetic field, particularly with a strong southward component, much more energy can enter the magnetosphere. A large CME can therefore look threatening and produce a less severe geomagnetic storm than feared. Another can arrive with magnetic conditions that make its impact much more effective. Size alone does not decide the outcome. Neither does speed. This is why the final stage of warning matters so much. Far upstream from Earth, spacecraft monitor the solar wind directly. When the disturbance reaches these monitors, instruments can finally sample the material that is about to strike the magnetosphere. The speed becomes measured rather than estimated. The density becomes visible, the magnetic field becomes visible, and the crucial orientation becomes much clearer. But by then, the remaining warning may be measured in tens of minutes rather than days. There is an odd imbalance here. Humanity can see the storm crossing much of the space between the Sun and Earth. Yet some of the information that most strongly determines the severity of the impact becomes certain only near the end. It is rather like watching a train approach from a great distance, while discovering rather late how heavily it is loaded. The earlier warning is still enormously useful. Nobody needs to wait until the last half hour to begin preparing. Space weather agencies can issue watches and warnings. Grid operators can review expected conditions. Satellite operators can alter plans. Airlines can consider routes. Maintenance can be postponed. Staff can be brought into position. The final measurements then determine how aggressively those precautions may need to be used. For the power grid, preparation is partly about creating margin. Electrical networks are normally operated to deliver power efficiently and reliably under expected conditions. During a serious geomagnetic threat, operators may prefer a system with more room to absorb disturbances. Power transfers can be adjusted. Certain equipment can be kept available rather than removed for maintenance. Additional reactive power support can be prepared. Operators can monitor geomagnetically induced currents and transformer behavior. Procedures developed specifically for geomagnetic disturbances can be activated. None of this is visually impressive. There is no enormous shield rising over a city. No machine points toward the Sunday. Much of the defense consists of people changing how other machines are being used. That is often what mature infrastructure protection looks like. A little less load here, a different configuration there, a postponed maintenance job, a person watching a measurement more closely, a transformer allowed more margin. The goal is not to defeat the storm. The goal is to prevent the disturbance from turning one stressed component into a sequence of failures. In some circumstances, operators may deliberately disconnect equipment or reduce service rather than risk damage. This creates an important distinction between a controlled outage and a destructive one. From a dark apartment, both look remarkably similar. The light does not work, but their futures can be completely different. If a section of the grid is temporarily de-energized to protect vulnerable equipment, the inconvenience may be significant, but the hardware remains available for restoration. If equipment stays energized through damaging conditions and suffers physical failure, recovery becomes harder. A few hours of deliberately reduced service can therefore be preferable to a much longer period waiting for repair or replacement. This is not a uniquely modern insight. Humans have been sacrificing immediate convenience to protect future capability for a very long time. Ships reduce sail before storms. Cities close roads before floods. Factories shut processes down when conditions become unsafe. A controlled retreat can preserve the thing you intend to use tomorrow. The power grid simply performs this logic at a scale large enough that millions of people may notice. satellite operators face their own version of the same choice. A spacecraft cannot be brought indoors. There is no garage in orbit, but its operations can sometimes be changed. Sensitive activities may be delayed. Certain systems can be placed into safer configurations. Operators may reduce unnecessary risk during periods of elevated radiation or charging. After the storm, spacecraft can be assessed and returned to normal operation. The precise options depend on the satellite. There is no universal safe mode that makes every spacecraft immune to space weather. But modern satellites are designed with the knowledge that the environment above Earth is not quiet. Radiation is normal there. Charging is normal. Solar activity is expected. Engineering is partly the art of deciding how abnormal conditions a machine should survive without making the machine impossibly expensive. That same compromise exists on Earth. We could theoretically build infrastructure with enormous spare capacity everywhere, duplicate every critical component, store vast quantities of replacement equipment, maintain enough generators and fuel to operate every service indefinitely, protect every system against the most extreme conceivable event. We generally do not. The cost would be extraordinary, and resources spent protecting against one rare hazard cannot be spent on everything else society needs. So engineers work with probability. How often might this happen? How severe could it reasonably be? What fails first? How expensive is that failure? How quickly can it be repaired? What protection gives the greatest reduction in risk for the cost? This can feel unsatisfying when discussing an event as dramatic as Carrington. People naturally want a yes or no answer. Are we protected or are we not? The real answer is distributed across thousands of pieces of equipment. Some are highly protected. Some are replaceable. Some have backups. Some are old. Some are new. Some sit in geologically vulnerable regions. Some do not. Some utilities have extensive experience with geomagnetic monitoring. Some systems face greater exposure simply because of their location and network design. Resilience is not a wall surrounding civilization. It is a collection of margins. And those margins have improved, partly because the world has already been warned several times. The Quebec blackout of 1989 was one such warning. It showed that geomagnetic disturbance could move from an interesting scientific phenomenon into the operating reality of a major power system. Later storms provided more experience. In October and November 2003, a period of intense solar activity produced what became known as the Halloween storms. Satellites experienced anomalies. Aviation operations were affected. High-frequency communication was disrupted. Navigation systems experienced problems. Power infrastructure faced geomagnetic effects, including serious transformer trouble in South Africa. The modern world did not collapse, but the event touched enough systems to make the interconnected nature of the risk difficult to ignore. Then came July 2012. The eruption missed Earth, but measurements from Stereo A showed that the Sun remained capable of producing an event of exceptional strength. This was a warning without a disaster, possibly one of the more useful kinds. Nothing needed to fail on Earth for scientists and engineers to study what might have happened under different geometry. Then May 2024 supplied another piece. This time, Earth was hit by a very strong storm. Auroras appeared at unusually low latitudes. Navigation and satellite operations experienced disruption. The storm reached the highest level on NOAA's geomagnetic scale, and much of modern infrastructure continued operating. That outcome should not be used to dismiss Carrington-level risk, nor should it be ignored because it fails to fit an apocalyptic story. It tells us something valuable. Modern systems can withstand substantial space weather. Operators can prepare. Forecasting helps. Engineering helps. The threshold between disruption and catastrophe is not crossed merely because an aurora appears far south. The system has room. The real concern is what happens when an event pushes beyond that room. This is why preparedness for extreme space weather increasingly resembles preparation for other low-frequency, high-consequence hazards. Utilities model scenarios. Governments develop response plans. Researchers improve forecasts. Engineers study transformer behavior. Spacecraft observe the Sunday. Ground instruments measure geomagnetic changes. Replacement strategies are considered. Information is shared across sectors because the grid, communications, transport, and emergency services cannot plan entirely in isolation. There is even a peculiar logistical problem surrounding the largest transformers. These machines can be so heavy that replacing one is partly a transportation project. Road capacity matters. Bridges matter. Rail access can matter. Specialized trailers may be required. A replacement transformer sitting safely in storage is useful only if it can reach the place where it is needed. This is why spare transformer programs and mutual assistance arrangements matter. Not every utility needs an identical replacement for every machine sitting beside every substation. Equipment can be positioned strategically. Plans can exist for sharing resources after major events. Transport routes can be considered beforehand. The temporary solution becomes planning rather than improvisation. And planning is one of the quiet differences between 1859 and today. The telegraph operators improvised because nobody had procedures for a geomagnetic superstorm. They disconnected batteries because the natural current entering the line had become strong enough to operate the equipment. Their response was empirical. Try something. See whether the line behaves better. Modern operators can still improvise when reality refuses to follow the manual, but they begin with more than that. They have monitoring, models, procedures, historical examples, exercises, communication with forecasters. The accumulated memory of previous failures has been turned into institutional behavior. That is one of the ways civilization becomes more resilient without anyone noticing. A disaster occurs. Someone writes a report. A recommendation appears. Equipment changes. A procedure is added. Years pass. The original event fades from public memory. The procedure remains. Then another event arrives, and a person follows a rule created because someone else had a very bad night decades earlier. History survives in checklists. Carrington survives in them too. But there is another level of preparation, much closer to home, where the problem can easily become ridiculous. Search for advice about surviving a solar superstorm, and it does not take long to encounter the end of civilization. Bunkers, years of food, Faraday cages for every electronic object, claims that cars will stop permanently, claims that every phone will be destroyed, claims that the electrical grid will certainly remain down for years. Claims that modern society will return overnight to the 19th century. This makes extreme space weather sound exciting. It does not necessarily make anyone better prepared. The useful personal response to a severe solar storm is much less exotic. It looks remarkably similar to preparation for an ordinary extended power outage. Water, food that can be stored without refrigeration, necessary medicines, flashlights, batteries, a way to receive emergency information, a modest amount of cash, charged power banks, a plan for household members who depend on electrically powered medical equipment, fuel handled safely where appropriate, knowledge of local emergency guidance. None of these requires believing that civilization is ending. They are useful during storms, floods, grid failures, and many other disruptions as well. The objective is not to become independent of society forever. It is to give society time to recover without every household immediately becoming an emergency. That is a very different philosophy of preparedness. A few days of supplies do not protect someone from every imaginable worst-case scenario. They reduce pressure during the most likely early stages of a serious disruption. If roads are crowded, you do not need to leave immediately for water. If payment networks are unreliable, you have another option. If the power is off overnight, you have light. If official information is being broadcast, you can receive it. If a phone cannot be charged from the wall, you have some stored energy. Small margins. Again, at household scale this time, the same principle used by the electrical grid. Resilience is often simply the ability to wait safely. There is also very little reason for the average person to spend the warning period desperately wrapping household electronics in improvised metal containers. A geomagnetic storm is not the same phenomenon as a fictional planet-wide electromagnetic pulse that instantly destroys every unshielded electronic device. The most serious terrestrial geomagnetic effects favour long conductors and large connected systems. Power grids are a concern precisely because transmission networks stretch over great distances. Pipelines can experience geomagnetically induced effects for similar reasons. A small, disconnected electronic device sitting in a drawer is not a miniature transmission grid. This does not make electronics invulnerable to every consequence of a severe storm. Devices can lose power. Networks can fail. Charging infrastructure can disappear. Satellite-dependent services can degrade. But the dramatic image of every unplugged phone and car being simultaneously fried is not a useful representation of geomagnetic risk. In fact, one of the most practical things a person could do after receiving a credible warning would be almost embarrassingly ordinary. Charge things. Charge the phone. Charge the power bank. If the household has larger battery storage, make sure it is ready. Check flashlights. Know where medications are. Avoid letting the car sit nearly empty if a significant regional outage is genuinely expected. Fill sensible gaps in ordinary emergency supplies. Then stop. Preparedness can become another form of anxiety if it has no stopping point. There will always be another object that might be useful. Another scenario. Another backup for the backup. At some stage, a household has enough margin to handle the realistic early disruption, and the remaining responsibility belongs to the larger systems around it. That is what civilization is for. No individual can personally maintain a power grid, water treatment plant, hospital, telecommunications network, satellite constellation, fuel distribution system, and food supply chain. The point of collective infrastructure is that we do not have to. Personal preparedness bridges the gap. It does not replace the bridge. And if our hypothetical Carrington-class storm were now only hours away, this is probably what the world would look like. Not panic everywhere. Not empty cities. Not people abandoning technology. Mostly ordinary life, continuing beneath a technical warning. Utilities adjusting their systems. Satellite operators watching data. Airlines reviewing routes. Emergency managers checking plans. Some people filling fuel tanks. Some charging batteries. Many doing nothing at all. News channels trying to explain magnetic fields with graphics. Social media producing the usual mixture of excellent information, complete nonsense, jokes, photographs of the sun, and people confidently announcing outcomes nobody can yet know. Then the upstream monitors would begin measuring the incoming structure. The numbers would sharpen. The magnetic field would turn strongly southward. Forecasters would know the storm had teeth. Warnings would become more urgent. Operators would make the decisions they had prepared to make. And then there would be very little left to do except allow the plans to work. The disturbance would reach Earth. The magnetosphere would compress and change. Currents would intensify. Some systems might fail. Others would disconnect deliberately. Satellites would experience difficult conditions. Radio would become unreliable in places. Auroras would spread. And the people who had spent the previous day hearing that something enormous was approaching would finally be able to walk outside and see evidence of it. The sky might turn red, just as it did in 1859, but almost everything beneath that sky would be different. Carrington's world had almost no warning and relatively little infrastructure to protect. Our world has extraordinary warning systems and extraordinary vulnerability. We built both at the same time, And that leaves one final question before the storm can pass. Not whether modern civilization is fragile, it is. Not whether it is invincible, it is not. The more interesting question is how often the sun actually asks us to find out. Because Carrington was extraordinary, but it was not unique. And hidden in tree rings, polar ice, old magnetic records, damaged transformers, and a handful of near misses is evidence that the sun has been testing Earth for far longer than we have had wires to notice. Because Carrington was extraordinary, but it was not unique. And hidden in tree rings, polar ice, old magnetic records, damaged transformers, and a handful of near misses is evidence that the sun has been testing Earth for far longer than we have had wires to notice. This creates an awkward problem when we try to decide how rare an event like 1859 really is. The technological record is extremely short. Electric power grids are younger still. Satellites have existed for only a few generations. Continuous measurements of the solar wind near Earth cover an even smaller fraction of human history. The instruments we would most like to have used during the Carrington event had not been invented. So if we ask how often the sun produces something worse than the storm of 1859, the modern record cannot answer by itself. It is rather like trying to estimate the largest flood a river can produce after watching it carefully for only a few decades. You can learn a great deal. You cannot safely assume that the largest thing you happened to witness was the largest thing possible. Carrington itself demonstrates the problem. For many years it became the reference point for extreme space weather because it occurred at precisely the right moment to leave several kinds of evidence. There were astronomers watching the Sunday. There were magnetic observatories recording disturbances. There were telegraph networks long enough to respond dramatically. There were newspapers capable of collecting auroral reports across wide regions. The world had just enough technology to notice. Go backward several centuries, and an equally strong geomagnetic storm would leave a very different record. There would be no telegraph operators describing sparks, no transformer data, no satellite anomalies, no measurements from spacecraft upstream of Earth. People would have seen the sky. They might have written about unusual lights, and then the event would have disappeared into history. This is why old descriptions of auroras have become useful. Researchers have examined chronicles, diaries, astronomical records, and other historical texts looking for unusual displays, especially observations made at low magnetic latitudes where auroras ordinarily would have been rare. The work is difficult. An old account of a red sky is not automatically an aurora. It might describe atmospheric optics, distant fire, weather, or something else entirely. Dates can be uncertain. Translations matter. Descriptions may have been written long after the observation. Historical observers did not use modern scientific categories, so individual reports require caution. But when multiple independent observations appear across different locations at similar times, especially alongside other evidence of solar activity, the case becomes stronger. One remarkable period occurred in September 1770, almost 90 years before Carrington. Historical records from East Asia describe auroral displays extending to unusually low latitudes over multiple nights. Some accounts describe intense red skies. The duration is particularly interesting. Carrington is remembered largely as a dramatic peak. The 1770 sequence suggests that extreme geomagnetic activity can persist or recur across several days when the sun produces repeated eruptions from a highly active region. That possibility changes the human problem. A single strong impact can stress infrastructure. Repeated impacts can complicate recovery. Equipment that has just endured one disturbance may face another. Satellite operators may remain in protective modes. Grid operators may have to maintain conservative configurations. The issue becomes not only intensity, but endurance. The sun does not promise to produce its difficulties one at a time. Then there is 1921. By then, The electrical world had grown. Telegraph and telephone systems were far more extensive than they had been in 1859. Railways relied on electrical signalling. Communication networks had become woven more tightly into commerce and transportation. In May of that year, a major geomagnetic storm produced severe disturbances. Telegraph systems were disrupted. Telephone equipment was affected. Electrical currents entered long conductors. Fires were reported in communication and signalling facilities. One of the most famous incidents involved railway infrastructure in New York State, contributing to the storm's later nickname, the New York Railroad Storm. The exact relationship between geomagnetically induced currents and individual fires must be treated carefully because historical reporting can simplify complicated electrical failures. But there is little doubt that the 1921 storm caused widespread technological disruption, and this gives us another useful progression. In 1859, the storm found telegraph wires. In 1921, it found a more developed electrical communications system. In 1989, it found a continental-scale power grid. In 2003, it found satellites, aviation, GPS, and modern electrical infrastructure. In 2024, it found a world containing enormous satellite constellations, precision agriculture, cloud computing, digital finance, and billions of connected devices. The sun keeps encountering a different civilization. That makes comparisons difficult. A storm does not have a fixed technological consequence. The consequence depends on what humans have built when it arrives. There is also a storm from 1872 that has attracted increasing attention. Auroras were reported at exceptionally low latitudes, including regions where such displays would have been extraordinary. Historical magnetic observations and auroral reports suggest a severe geomagnetic event that may belong in the same broad conversation as 1859 and 1921. This is important because it weakens the comforting image of Carrington as a solitary monster surrounded by centuries of quiet. Within roughly 6 decades, the 19th and early 20th centuries produced several events capable of creating remarkable low-latitude auroras and technological disturbance. That does not mean Carrington-class storms occur every few decades with predictable regularity. Solar activity does not operate like a railway timetable, but it does mean the historical record contains more than one warning. Then, in 1989, Quebec went dark. In 2003, the Halloween storms caused broad disruption. In 2012, Earth narrowly avoided the direct path of an exceptionally powerful eruption. And in 2024, another major geomagnetic storm reminded millions of people that auroras are not confined permanently to postcards from the Arctic. Taken together, these events make one thing difficult to argue. Extreme space weather is not hypothetical. The uncertainty lies in frequency and severity, not existence. But the most unsettling evidence does not come from telegraph offices or magnetic observatories. It comes from trees. A tree is not an obvious solar observatory. It does not have an antenna. It does not record magnetic fields. It does something much slower. Every year, while it grows, it incorporates carbon from the atmosphere. Most atmospheric carbon is ordinary carbon, 1,2. A small fraction is radioactive carbon, 1,4. Carbon, 1,4, is continually produced when energetic particles ultimately create neutrons in Earth's atmosphere, which then interact with nitrogen. The amount can change when Earth is exposed to unusual bursts of high-energy particles. Once carbon enters the atmosphere, and then living plants, part of that chemical history can become fixed in annual growth rings. The tree does not know it is recording anything. It simply grows. Centuries later, someone cuts or cores the wood, separates individual rings, measures their chemistry, and discovers that one particular year contains an abrupt increase in carbon, 1,4. In the early 2010s, researchers studying Japanese cedar trees found something extraordinary. The rings associated with the years 774 and 775 showed a sharp increase in radiocarbon. It was too large to fit comfortably within ordinary year-to-year variation. The finding was initially strange enough that multiple possible explanations had to be considered. Then similar signals were found in trees from other regions. Evidence from other cosmogenic isotopes, including records preserved in polar ice, supported the conclusion that Earth had experienced an enormous influx of energetic particles. The event became known as the 774-775 event, or more broadly as one of the Miyake events, named after researcher Fusa Miyake, whose work helped reveal this new category of extreme particle event in annual tree rings. The discovery changed the scale of the conversation. Carrington had been visible to 19th century technology. The event recorded in those trees occurred more than 1,000 years earlier. There were no electrical grids to fail, no satellites, no telegraph lines. The atmosphere absorbed the event, chemistry changed slightly, trees continued growing, and the evidence waited inside wood. That is an unusually quiet way for a violent solar or cosmic event to survive. For centuries, people could have held pieces of the evidence in their hands without knowing what they contained. Roof beams, old timber, archaeological wood. A year in which the atmosphere changed was preserved as a thin layer between two ordinary years. Researchers have since identified other abrupt cosmogenic isotope events in the past. Another significant event occurred around 993-994. Additional candidate or confirmed events have been found deeper in the record, including examples thousands of years old. These discoveries have turned tree rings into something more than climate records. They can act as calendars for extreme events in near-Earth space. They have even become useful for archaeology. If a piece of ancient timber contains the distinctive radiocarbon signature of a known event, researchers can count rings outward or inward from that marker, and sometimes establish extraordinarily precise dates for when the tree was cut. A solar disturbance can therefore become a timestamp. Something that may once have filled the upper atmosphere with energetic particles can later help date a wooden structure. History has a sense of recycling, but the Miyake events create an important danger of misunderstanding. They are not simply prehistoric Carrington events. The Carrington event is known primarily as an extreme geomagnetic storm associated with major solar activity. The 774-775 event is identified through a large increase in cosmogenic isotopes, indicating an extreme energetic particle event. Those phenomena are related to solar activity, but their severity cannot be translated directly from one to the other. A solar eruption can produce a strong geomagnetic storm, a strong solar energetic particle event, or both, depending on its characteristics and geometry. So it would be misleading to say that the 774 event was definitely 10 times Carrington and would therefore produce 10 times the transformer damage. Nature does not provide that conversion. What the tree rings tell us is subtler. The Sun, or in some debated cases another high-energy astrophysical source, can produce particle environments far beyond what has been directly measured during the satellite era. For the best-studied Miyake events, extreme solar activity is generally regarded as the leading explanation. That matters greatly for satellites, astronauts, high-altitude aviation, radio communication, and the broader question of how violent solar activity can become. But it does not allow us to reconstruct a medieval power grid failure that never existed. The distinction is important because this subject attracts very large numbers. A study estimates an event several times stronger than something else. The number escapes into popular culture. Soon an ancient tree ring is predicting the end of the internet. The original science was usually more careful. The tree is telling us that something extreme happened. It is not writing a disaster screenplay. There is another complication. The Sun follows an approximately 11-year activity cycle, moving between periods of relatively low and high sunspot activity. This cycle is real and useful. It is not a countdown to catastrophe. Solar maximum increases the likelihood of significant flares and eruptions because there are more active regions capable of producing them. But an 11-year cycle does not mean an extreme storm arrives every 11 years. Most solar maxima pass without anything resembling Carrington. Even within active periods, Earth has to be in the right place. The eruption must be directed toward us. Its speed matters. Its magnetic structure matters. Previous solar activity can alter the space through which it travels. Then, Earth's own magnetic and geological environment helps determine the consequences. The chain contains many conditions. This is why estimating recurrence is difficult. Researchers use historical observations, cosmogenic isotopes, solar physics, statistical models, and modern measurements to estimate the probability of extreme events. Different studies produce different numbers depending on how Carrington-like is defined and what evidence is included. Some estimates have suggested that the chance of a Carrington-scale event occurring within a decade is not negligible. Other analyses produce lower probabilities. There is no universally accepted calendar saying the next one is due, and the phrase overdue is particularly unhelpful. The Sun does not know how long it has been since 1859. Rare random events do not become obliged to occur because humans have waited a while. A century and a half without another clearly equivalent direct hit does not mean one must happen soon. It also does not mean one cannot happen tomorrow. That uncertainty is uncomfortable because people prefer risks that behave on schedules. Seasonal storms arrive in seasons. Tides can be calculated. Eclipses can be predicted with extraordinary precision. Solar eruptions are not like that. We can identify active regions. We can estimate probabilities of flares. Once a CME is launched, we can forecast its arrival. But we cannot look at the calendar and name the date of the next Carrington event. There may be decades of relative quiet. There may be several severe events within a comparatively short period. The historical record appears to contain clusters as well as long gaps. This brings us back to July 2012. That event matters not because it proves catastrophe was narrowly avoided in every imaginable sense, but because it occurred during the modern observational era and was measured by a spacecraft in its path. A powerful CME erupted from the Sun and travelled rapidly through interplanetary space. Earlier eruptions appear to have conditioned the region ahead of it. The event reached stereo A, allowing researchers to measure an unusually intense combination of solar wind speed and magnetic field. Had Earth been positioned differently, it could have produced a severe geomagnetic storm here. The phrase often used afterward was near miss. It is useful if handled carefully. Earth was not dodging anything. The eruption occurred where it occurred. Our planet happened not to be in its path. But the event demonstrated that the physical ingredients associated with extreme space weather still exist on the modern Sunday. We did not leave the Carrington era behind. We electrified ourselves more thoroughly inside it. And yet this realization can be strangely calming. The Sun is not becoming hostile. It has always been active. Human beings simply became capable of noticing more of what it does. The red skies of 1859 were not a warning that the natural order had broken. They were the natural order. The telegraph operators had accidentally placed a new kind of instrument inside that order, and the Sun revealed a vulnerability they did not know they had. Every generation since has repeated some version of that experience. Build something. Depend on it. Discover a condition its designers did not fully anticipate. Adapt. The early telegraph had problems with geomagnetic currents. Power grids developed procedures. Satellites encountered radiation and charging. Designs improved. Navigation systems encountered ionospheric disturbance. Models improved. forecasting improved. None of these adaptations removes the hazard. They change the relationship with it. This is how humans have lived with natural extremes for a very long time. We do not stop earthquakes. We change building codes. We do not stop hurricanes. We forecast them, evacuate when necessary, strengthen structures, and build emergency systems. We do not stop rivers from flooding everywhere. We build levees, reservoirs, warning systems, and maps, sometimes successfully, and sometimes with consequences of their own. The sun is simply a much larger piece of weather. Its atmosphere extends outward through the solar system. Earth lives inside it. Most days, this fact is invisible. Occasionally, the sky reminds us. And if a Carrington-class storm arrived in our lifetime, the experience would probably contain both familiarity and novelty. We would recognize the warnings. Scientists would understand the broad mechanism. Engineers would know which systems deserved attention. The public would have access to information Carrington could never have imagined. But we would still learn something new. Every extreme event finds the edge of our models. There would be some transformer that behaved differently than expected, some satellite anomaly that became a case study, some region that performed better than predicted, another that performed worse, some procedure that proved valuable, another that would be rewritten afterward. Reports would be published, standards would change, equipment would be modified, the storm would become part of the memory of infrastructure. And decades later, someone might follow a procedure without knowing it had been written because of that particular night. That is the quieter meaning of the historical record. 1859 is not useful because it tells us exactly what will happen. It cannot. The modern world is too different, and our measurements of Carrington are too incomplete. It is useful because it revealed the category of problem. 1921 confirmed that the problem did not belong to one night. 1989 demonstrated that electrical grids could be affected. 2003 showed the reach of space weather across modern technology. 2012 demonstrated that very powerful eruptions still occur. 2024 gave modern operators a large real-world test. The ancient isotope events stretch the scale backward beyond all of them. Together, they give us something better than certainty. They give us evidence. And evidence allows preparation without prophecy. This is probably the most useful place to leave the question of frequency. The next great storm is not scheduled. It is not waiting for a particular anniversary. There is no countdown hidden inside the solar cycle. It may arrive during a period when people are paying close attention to the Sunday. It may arrive after years of public indifference. It may produce spectacular auroras and limited disruption. It may become the event against which future engineers measure everything else. We cannot know beforehand. What we can know is that Earth has been here before, long before Richard Carrington entered his observatory, long before anyone stretched copper wire between cities, long before a transformer stood beside a transmission line, long before the first radio signal, the first satellite, the first GPS receiver, the first server farm, the sun erupted. Particles crossed space. Earth's magnetic field moved. Auroras spread across the sky. Then the disturbance passed. Forests kept growing. Oceans moved. People woke the next morning. The difference now is that we have built a civilization sensitive enough to feel the storm in ways our ancestors could not. But we have also built instruments sensitive enough to see it coming. And so, after all the red skies, sparking wires, failed grids, satellites, warnings, and ancient traces preserved inside trees, we can finally return to the question we began with. Whether one strange night in 1859 really wrote the playbook for the end of the modern world, or whether it left us something far more useful, a warning about how to keep it running. Whether one strange night in 1859 really wrote the playbook for the end of the modern world, or whether it left us something far more useful, a warning about how to keep it running. By the time the great storm of 1859 began to fade, the most dramatic part had already passed. The sky no longer looked as though some enormous fire had been lit beyond the horizon. The auroral bands weakened. Telegraph equipment stopped behaving quite so strangely. The currents that had entered long wires diminished as Earth's magnetic environment settled. Morning came, and morning, after a night like that, must have felt almost suspiciously ordinary. The sun rose. People went back to work. Telegraph offices resumed familiar routines. Newspapers printed reports from towns and cities where witnesses had spent the night trying to describe what they had seen. Some people would have regarded the whole thing as an extraordinary curiosity. Others had been frightened. Some had probably slept through much of it. That is worth remembering. Historical events rarely arrive with equal force for everyone. One person witnesses the sky turn red. Another only hears about it the next day. One telegraph operator fights a line full of unwanted current. Another office experiences less trouble. One observer sees an aurora so bright that it seems to alter the night. Another lives under cloud. And even when an event is planetary, human experience remains local. What changed after 1859 was not the Sunday. It was our understanding of what had happened. Carrington's observation became part of a larger body of evidence connecting solar activity with magnetic disturbances at Earth. The telegraph disruptions became more than mechanical oddities. The auroras became more than beautiful or frightening lights. The separate pieces slowly became one system. That process took time, and it is easy, looking backward, to underestimate how important that was. Before the connection was understood, the event was strange. After the connection was understood, it became a problem. Problems can be studied. They can be measured. They can be anticipated. They can be designed around. Not perfectly, but enough to change the outcome. That is the real distance between 1859 and now. Not simply the distance between telegraph wires and satellites. The deeper difference is that we no longer have to discover the storm by touching the machine that is already malfunctioning. We can watch the Sunday. We can see an eruption leave. We can estimate its path. We can measure the solar wind before it reaches us. We can warn operators. We can prepare systems. We can decide to accept temporary inconvenience in order to avoid larger damage. The danger remains physical. The response has become partly informational. And information, when it arrives early enough, can be one of the most effective forms of protection. This does not mean a future Carrington-class event would be easy. It may not be. A very severe storm could cause widespread operational problems. Some electrical systems could experience major stress. Some regions could lose power. Satellites could be affected. Navigation could become less reliable. Aviation could face communication and routing difficulties. If physical damage became significant, some outages could last much longer than an ordinary blackout. Water, fuel, food distribution, healthcare, and communications could all become harder to manage in the areas most affected. Those risks are real enough that they deserve serious planning. But serious planning is not the same thing as assuming the worst case is inevitable. That distinction matters because the Carrington event has gradually become two stories. The first is historical. An astronomer sees an extraordinary flash on the Sunday. A geomagnetic storm reaches Earth. Auroras appear at unusually low latitudes. Telegraph systems are disrupted. Operators discover that induced currents can power lines even after their batteries are disconnected. This story is strange because it happened. The second story is modern mythology. One day, the sun erupts. Every transformer explodes. Every satellite falls. The internet vanishes. Cars stop. Phones die. Power disappears for years. Civilization immediately returns to some vaguely imagined 19th century. This story is dramatic because it compresses many different vulnerabilities into one moment. It is also much less useful. The real danger is slower and more uneven. A grid under stress. A satellite temporarily unreliable. A communication route unavailable. A hospital shifting to backup generation. A fuel station that cannot pump. A water system using reserves. A household watching battery levels. A city waiting for restoration. These are less spectacular than a global electronic apocalypse. They are also much closer to the kinds of problems engineers and emergency planners can actually reduce. That is one of the quiet benefits of replacing myth with mechanism. Mechanism gives you somewhere to act. If the problem is the sun destroys civilization, there is not much to do. If the problem is induced current in long transmission networks, then grid configuration matters. Transformer design matters. Monitoring matters. Warning matters. If the problem is satellite drag, orbital forecasting matters. If the problem is GPS degradation, alternative navigation and timing systems matter. If the problem is prolonged blackout, fuel planning, water resilience, backup generation, and restoration procedures matter. Specific problems are less emotionally satisfying than vague doom. They are much more solvable. And this is where Carrington becomes unexpectedly reassuring. Not because the storm was mild, it was not. Not because modern civilization is invulnerable, it is not. But because the event was observed early enough in the electrical age that it gave us a category of risk before electricity became the foundation of almost everything. It was a warning delivered to a civilization that had only begun building the systems that would later need protecting. The telegraph operators of 1859 could not have known this. To them, the strange current was a nuisance, a danger, and in some cases, an opportunity. If disconnecting the battery made the line work better, then disconnect the battery. Practical people solve the problem in front of them. They did not need to understand the magnetosphere to discover a temporary solution. That improvisation has a modern echo. During a future storm, grid operators may disconnect or reconfigure parts of a system to protect equipment. Satellite operators may place spacecraft into safer modes. Aircraft may change routes. Businesses may reduce operations. Households may use stored water, batteries, cash, or food that does not require refrigeration. The scale is different. The principle is familiar. When the normal system becomes unreliable, you reduce dependence on it until conditions improve. Then you restore. This is not the end of civilization. It is one of the things civilization does. It bends, sometimes badly. Then it tries to return. And recovery, when it begins, is usually much quieter than failure. The first successful restoration may happen in a control room long before anyone notices. A line is energized. A transformer holds. A generating unit synchronizes. A communication site reconnects. A pump restarts. A satellite returns to normal operation. A route reopens. A hospital stops consuming backup fuel as rapidly. Then the changes reach ordinary life. A hallway light comes on. An elevator moves. A router begins blinking. A phone finds a stronger signal. A refrigerator starts humming. Water pressure improves. A card terminal accepts a payment. A petrol pump works. A traffic signal changes colour. These are tiny events. Normally, nobody would consider them worth noticing. After disruption, they become evidence that the larger system is healing, and there is something instructive in that. Modern civilization feels enormous when it is functioning. During recovery, it reveals itself as millions of small functions returning one by one. The same is true in reverse. The end of normal life rarely begins with one enormous failure. It begins when enough small things stop being dependable. That was the deeper lesson hidden inside the telegraph office. The current did not destroy the world. It revealed dependence. The operators expected electricity to come from one place, the battery. The storm introduced electricity from somewhere else. That simple contradiction made the system difficult to control. Our world is filled with much more elaborate versions of the same expectation. We expect power from the wall, timing from satellites, communication from networks, water from taps, money from digital systems, food from supply chains, navigation from screens. Most of the time, those expectations are justified. The systems are remarkably good. The fact that we stop noticing them is one of their greatest achievements. But invisibility creates surprise. Carrington reminds us that every invisible system is still attached to the physical world. The cloud is buildings and cables. GPS is clocks in orbit. The electrical grid is copper, aluminium, steel, magnetic cores, substations, and geology. The internet is glass fiber, routers, landing stations, cooling systems, and power. Satellites fly through a real atmosphere whose density changes. Radio signals pass through a real ionosphere that can become disturbed. Modern life does not float above nature. It is built inside it. That sounds less like a warning once you sit with it for a while, because nature is exactly what engineering understands best when it has enough evidence. The sun does not hate the grid. The magnetosphere does not attack satellites. The upper atmosphere does not decide to interfere with navigation. These systems follow physical rules. The rules may produce severe consequences when conditions become extreme, but they remain rules, and rules can be studied. The most frightening kind of hazard is one that remains mysterious. Carrington is no longer mysterious in the way it was to the people living through it. There are still uncertainties. The exact intensity of the 1,859 storm remains debated. Its precise solar particle environment cannot be reconstructed perfectly. We cannot know exactly what the same event would do to every modern grid. We cannot predict the date of the next comparable storm. But uncertainty is not ignorance. We know enough to build warnings, enough to identify vulnerable systems, enough to prepare, enough to avoid some of the mistakes that would otherwise turn a severe event into a larger one. And perhaps most importantly, we know enough not to confuse spectacle with consequence. The red sky is not the disaster. It is the visible part. An aurora can be magnificent, while infrastructure remains stable. A serious grid problem can occur beneath clouds, where nobody sees anything beautiful at all. The colour overhead tells only part of the story. The important measurements may be happening inside a transformer, a satellite, a control room, or a spacecraft far upstream of Earth. This changes how we should think about fear. If the aurora spreads far south one night, fear is not automatically the appropriate response. Attention is. Listen to reliable warnings. Understand what services may be affected. Prepare for ordinary disruptions. Then, if conditions are safe, look outside, because even during an extreme storm, the aurora itself is not an enemy. It is evidence. The atmosphere glowing because particles and magnetic fields are interacting above us. A visible reminder that Earth is not isolated. Our planet lives inside the environment of a star. It always has. Long before Richard Carrington, long before the telegraph, long before human beings, the solar wind moved past Earth. The magnetic field responded. Auroras appeared. The atmosphere absorbed radiation. Trees grew. Oceans moved. Night became morning. Most of this happened without anyone watching. Then humans appeared and began paying attention. We watched the sky. We learned to measure time from it. We learned to navigate by it. We learned to study the Sunday. Then we built instruments sensitive enough to notice what had always been happening. That is another way of looking at the entire story. The Carrington event did not create a new danger. It revealed an old environment to a new technology, and every generation afterward has revealed another part of the same relationship. The telegraph revealed induction, power grids revealed transformer vulnerability. Satellites revealed radiation and drag. GPS revealed ionospheric dependence. Precision agriculture revealed how deeply satellite timing could enter something as ancient as planting a field. Data centers and digital networks revealed that the most modern parts of civilization still depend on physical power and cooling. None of this means progress was a mistake. That would be a very strange conclusion. The same technologies vulnerable to space weather have made modern life longer, safer, faster, and more connected. Electric grids support hospitals. Satellites warn us about hurricanes. Navigation helps aircraft travel safely. Communication allows emergency coordination. Data networks move knowledge instantly. The point is not to abandon dependence. It is to understand it, and to leave enough alternative paths that one failure does not become every failure. That is what resilience looks like, not independence. Options. One communication method fails, another remains. The grid fails, backup power starts. A digital payment fails, cash exists. GPS degrades, other navigation procedures remain. A satellite fails, another covers part of its function. A transmission path is lost, power reroutes. A neighborhood needs help, another can provide it. The systems become stronger when failure has somewhere else to go. The same is true socially. A neighbor checking on an older person is redundancy. A community cooling center is redundancy. A radio network is redundancy. A hospital with fuel reserves is redundancy. A spare transformer is redundancy. Redundancy looks inefficient during normal times. Then normal times stop, and suddenly inefficiency becomes survival margin. This is why the most sensible preparation for a severe solar storm looks so ordinary. A little water, food that keeps, necessary medication, light, a charged battery, some cash, a way to receive information, a plan for someone who needs electricity medically. Nothing more dramatic is required for most households unless local authorities advise otherwise. That is not because an extreme solar storm could never become severe. It is because the individual cannot solve the geomagnetic storm. The individual can solve the first few days of inconvenience. That is enough. The grid belongs to grid operators. Satellites belong to satellite operators. Water systems belong to utilities. The sun belongs to no one. The household has a smaller job. Stay informed. Create some margin. Do not become an emergency before you have to. Then allow larger systems to work. This may sound almost disappointingly calm after spending so much time with red skies and failing infrastructure. That is intentional. The goal of understanding risk is not to remain frightened by it. It is to know where fear is useful and where it is not. Carrington is worth remembering because it sits at the beginning of that process. A man observing the sun saw something strange. A network of wires behaved in ways their operators did not expect. People across the world watched the sky, and gradually an invisible connection became visible. More than a century and a half later, we can follow that connection almost from beginning to end. A magnetic region forms on the Sunday. Energy builds. A flare erupts. A CME may follow. The cloud travels through interplanetary space. Spacecraft detect it. Forecasters estimate arrival. Upstream monitors measure the magnetic field. The magnetosphere responds. The aurora expands. The ionosphere changes. The upper atmosphere heats. Currents are induced at the surface. Long conductors respond. Human systems absorb the disturbance as well as they can. Then the CME passes. Conditions settle. The aurora retreats. The grid returns to ordinary operation. The planet keeps turning. This chain sounds almost calm when we can see all of it. That is one of the rewards of explanation. The event loses none of its scale, but it becomes less like a supernatural interruption and more like part of a living planetary system. And if another great storm comes, some part of the experience will probably look remarkably similar to 1859. People will go outside. Someone will call another person and tell them to look up. Somebody will assume the photographs are exaggerated. someone will photograph the sky anyway. Children will be woken. There will be people who have waited their entire lives to see an aurora. There will be others who look at the colour and feel uneasy because they know what it may mean for the systems below. Engineers will work through the night. News reports will struggle to explain magnetic fields. Rumours will move faster than useful information. And eventually, if the storm is severe enough, some lights may go out. Then people will do what people usually do. They will check on one another. They will find flashlights. They will wait. They will complain. They will improvise. They will restore what can be restored. They will learn what failed. Reports will be written. Equipment will change. The event will become history. And one day, decades later, somebody will tell the story quietly at night. By then, perhaps the storm will have its own name. People will compare it with Carrington. They will debate which was stronger. Scientists will refine the measurements. Engineers will point out that the comparison is more complicated than the headline suggests. And somewhere in the discussion, the old telegraph will appear again. The batteries disconnected. The line still working. Because that image has survived for a reason. It contains the whole story in miniature. Human beings had built a system and assumed they understood where its power came from. Nature revealed a larger circuit. That is what Carrington gave us. Not a preview of inevitable collapse. A correction to our sense of scale. Our machines are powerful. Our networks are vast. But they remain inside a world larger than they are. Once that becomes clear, the correct response is neither arrogance nor panic. It is attention, and then preparation, and then, eventually, calm. So if you are listening late tonight, somewhere far from 1859, the chances are that everything around you is behaving normally. The lights are steady. Your phone has signal. Water waits behind a tap. Satellites are crossing overhead, whether you can see them or not. Power is moving through lines you are not thinking about. The sun is roughly 93 million miles away. Its surface is active. Magnetic fields are shifting. The solar wind is flowing. None of this is unusual. That is simply the environment in which Earth lives. And perhaps that is the gentlest way to leave the Carrington event. Not with the end of the modern world, with a quiet room, a functioning wire, a dark sky, and the knowledge that somewhere beyond it, the sun is still turning.